Hello. Okay. Hello, everyone. Good morning. Thank you for being here this morning. We're going to start with the first lecture of the day. We have Marta Pita Vidal with us. She's an experimentalist researcher at IBM. She works on the development of superconducting qubit-based quantum processors. In particular, she focused on transmon readout and leakage mitigation. Before that, she did a postdoc at IBM as well, working on germanium quantum dot spin qubits. And prior to that, during her PhD at QTech in the Netherlands, she developed hybrid qubits based on the combination of superconducting circuits with semiconducting nanowires. She has also worked on 2D materials at MIT and also at ICFO in Barcelona. So thank you very much, Marta, and the floor is yours.
Thank you. Thanks so much for the introduction. So good morning, everyone. Welcome, and thanks for being here this early in the morning. In this lecture, we are going to discuss how to implement a quantum computer using superconducting qubits. And to do that, I like to go from the very fundamentals, the building blocks of what elements one needs to create a resonator, a transmon, to what challenges appear when you try to implement it experimentally, as well as what are the next steps that the community is looking into going in the near future. So to do that, we'll have a two-part presentation. The first part is a bit more generic about all of these fundamental topics and some of the challenges. And on the second part, I'd like to go into what are the steps towards achieving fault tolerance at scale. And for this second part, we'll take as an example the approach that IBM Quantum is using to do so, so the next planned steps that we have for that. This first part is a bit more generic, and let's start with that. So what does one need to implement a quantum processor? The first thing you need is to put together a bunch of qubits. And with these qubits, you need to be able to encode any quantum state of the n qubits. So for one particular qubit, this would mean that you have to have a well-defined 0, a well-defined 1 state, and also that your qubit has to be in any of the possible superpositions of these 0 and 1 state. So basically everywhere, anywhere on the block sphere. The architecture should be scalable, meaning you should be able to increase and keep increasing the number of qubits without running into any unsolvable problems by doing that. It should also be possible to initialize the system, meaning deterministically one should be able to start the quantum state of the entire system at some concrete state, which typically one would choose to have the state for which all of the qubits are in 0 to get started. And there should be a method to do that reliably and reproducibly. Fourth, a quantum state should be encoded for long enough. And by this, I mean, I'm talking about the coherent states of the qubits. They should be very long compared to whatever operations you want to do on them. These operations could be singular to qubit gates, but also read out and any other operation that you want to do. So this coherence time should be much longer than that. Also, one should be able to perform any arbitrary calculation on this multi-qubit system. And this is something that can be achieved by using any single qubit rotations together with one entangling 2-qubit gate. And finally, we should have a way of measuring the state of the qubit. This should be possible to do. This should be compatible with the scalability requirement, and also it should be possible to do it with high fidelity, meaning if you have if your quantum state collapses to a 0 while measuring, you should read out a 0 when you try to read it out, and if it's a 1, a 1. So these are, by the way, not exactly, but very related to the DiVincenzo criteria. And I just wanted to mention that DiVincenzo, when he came up with this criteria some years ago, he was actually working at IBM. So that's just so you know that there is also quite fundamental basic research within the company. So now, in particular, superconducting circuits, why do we like them why are they so fashionable to build quantum processors? Main reason is that they fulfill all of the bullet points that we saw in the previous slide. And I'm not going to explain them now one by one, but they will come throughout the next few slides. And moreover, there is this practicality shown here. So there are also some practical reasons why we actually like superconducting qubits a lot. The first of them is that they operate in the microwave regime, meaning that the qubit frequencies are typically of the order of a few gigahertz. And the coupling interactions between qubits are of the order of like a few hundred megahertz, so a fraction of a gigahertz. This is also the frequency regime at which some other well-established technologies work already, such as radar, space technologies, and some other ones, which means that there's already plenty of connectors from temperature electronics, generators, cables that exist and that can be leveraged to work with superconducting qubits. So even though many of these have to be adapted to work with superconducting qubits, this allows one to already start with a threshold that's much lower than if it was a completely different frequency regime. And second, if you go and translate this microwave frequency, so gigahertz, into a time scale, so if you take the inverse of that, you get time scales of the order of a few nanoseconds or a few tenths of nanoseconds, which means that all of these interactions between qubits and also qubit manipulation can happen really fast. So the system can evolve quite quickly. So this is also one of the advantages of the frequency regime. Second, about the flexibility, this is a platform where we work with superconducting qubits, where you can write your Hamiltonian, translate it into an effective circuit model formed by some idealized capacitor, some idealized inductor, maybe a transmission line, and so on. And then you can just design that, put two pieces of metal with a certain capacitance, an inductor with certain inductance, and it actually behaves practically the same as what you simulated. So there is, it's a very clean system to work with in that whatever Hamiltonian you design, or not whatever, but you can design a Hamiltonian and build it, and it will be what you wanted. So this helps a lot building something that works. Moreover, both in this area of design and manufacturing, we have already plenty of tools from the classical computing area, such as EDA design tools, or also nanofabrication techniques, and many of them are compatible or quite easily adaptable to working with superconducting circuits. So that's also something that lowers the bar to get started. And finally, this comes directly from the name. They're superconducting, so they're inherently low loss. These qubit states are encoded in fluctuations of voltages and currents in a circuit, and they have to stay coherent for a while. If our metal was lossy, then they would quickly decay, and you would lose the information. So it's nice that they are superconducting, so that doesn't happen. These advantages also come with a price to pay, as always. So we end up having to operate these type of processors at very, very cold temperatures. One of the reasons for that is that they are superconducting, so you have to keep your material superconducting during the operation, and this forces you already to operate at a few Kelvin or below the 1 Kelvin regime. And moreover, precisely because of this microwave regime that we are operating at, if you now, instead of translating this to time, you translate it to temperature, you realize that 1 gigahertz is of the order of a few tenths of millikelvin, meaning if there are thermal excitations in your system, also if your system is hot and there is noise with a temperature of a few hundreds of millikelvin or a few Kelvin, this can unwantedly populate your system and make it leak or so. So this is also one of the reasons why, not only the superconducting part, but also the fact that this way we are exposed to much, much lower levels of noise. So with this, we turn now to a bit more of a technical part, taking a bit more in detail at how these elements that we see here in the image look like. So I just anticipate this is a transmon qubit that's coupled to a meandering superconducting resonator, but let's describe them a bit more mathematically now. So we first start with the meandering part, which is the LC resonator. These type of resonant objects can be implemented either with, in many different ways. So whatever resonates can often be well described as an LC oscillator to some level. We typically have structures such as this distributed one, where you have a central conductor that has a certain self-inductance per length, a capacitance to ground per length, and a certain total length that determines a resonance frequency. You can also have really like two pieces of metal that have some certain capacitance to each other and some inductor in between, and this will also have a characteristic resonance frequency. Either one of these objects one can model quite well with this circuit that we have here on the top left, which is an LC oscillator with simply just one capacitor and one inductor in series, in parallel. And if we want to investigate a bit better what are the properties of this object, it's convenient to define these quantities, such as the charge Q across the capacitor, the voltage V across the capacitor, the current I that flows through the inductor, and also the magnetic flux that's generated by this inductor. So now you can do a bit of math and write down the relationships between the derivatives of these quantities and also like the constraints imposed by the capacitor and the inductor. And the goal of this would be now to like learn about the resonance frequencies of these objects. And if you remember your classical mechanics course at the beginning of the bachelor, you might remember, I guess at least for the ones that studied physics, maybe not everywhere this is done, but there is this protocol of Lagrangian mechanics where you start writing the energies and end up having your Hamiltonian, right? So something that we can do is write down the energy stored in this system as a function of one of the variables, for instance, the flux through it. So the energy stored in the capacitor and inductor look like the ones here. And again, remember in that course, something that one would typically study would be a system such as the one shown here, where you have a spring with a spring constant K attached to a mass, and then this has some self-resonant modes that depend on the quantities and on the variables in the system. And this object actually is defined by some kinetic energy and potential energy as a function of the displacement x of this spring that resonates. And you can actually make a perfect analogy between the two systems. So the physics behaves exactly the same way if you compare your flux variable to the x displacement, if you assign your capacitance, if you interpret it as a mass, or if you interpret the inverse of your inductance as the spring constant. So already you can take all of the learnings that you have, if you remember about this spring system, such as, for instance, that its resonance frequency is the square root of k over m, and translate them directly to learn something about your resonator system, such as, for instance, the fact that its resonance frequency is the square root of 1 divided by LC. I have to confess, after working with these superconducting circuits for a while, this is much more intuitive to me than that part, but I just wanted to show it in case any of you remembers these spring systems, because it's really like whatever you remember from that already applies automatically to superconducting resonators. If you want to do it a bit more like technically, you can write down your Lagrangian, which is your effective kinetic energy minus your effective potential energy. From that, there is these Lagrange equations that you can do to end up conversion to a Hamiltonian that typically for this case turns out to be the sum of the two energies. And this is the object that you would diagonalize to obtain the resonant frequencies of the system. In the area of quantum computing, one would typically redefine these renormalized constants, a phase phi, which is a renormalized flux in units of 2 pi, and a renormalized charge n, which is basically the charge across the capacitor divided by twice the electron charge. So it's the number of Cooper pairs in this, across this capacitor. And one can also define this characteristic inductive and capacitive energies of the two objects. I'm just putting here the same Hamiltonian that we had, but rewritten in terms of these energies, because this is something that you encounter always in scientific papers, and it will also come back later in this presentation. And if you go and diagonalize that, as we were saying, now you can have, you end up having these horizontal lines are the eigenstates of the system. So the eigenenergies of the different eigenstates of the system with either 0 excitation, so the ground state, 1, 2, 3, and so on. And these live, as we were saying, in this parabolic potential as a function of phase, which comes from the 1/2 of EL times phase square. If you drive your circuit, your LC oscillator, with a certain frequency, and you choose that to be resonant with the 0 to 1 transition, you will excite excitations up to higher energy levels. But and one could think that we already have something that looks very similar to a qubit here, right? We have a 0 state and a 1 state. The problem is that these eigenenergies for a perfectly harmonic LC oscillator are equidistant from each other. So if you try to drive them with a frequency, you will unavoidably start exciting also the higher energy states. You end up having a Poissonian distribution of population. So you cannot really operate this as a qubit, because you cannot make sure that your state really stays on the 0 and 1. It will unavoidably go up. Just again, to rewrite once more this Hamiltonian in a different basis, something that is very convenient is to use the ladder operators, A dagger and A. So A dagger is an operator that takes some state and brings it up to 1 state higher, and A does the opposite. And this will again come back later. So I just wanted to mention that they exist if you haven't seen them before. And basically, since this is an harmonic, you just have that your Hamiltonian is the number operator, A dagger, so that takes value n for state n, times the frequency. So that's why it goes up 1 by 1 for the different states. Now, this is very convenient, and we will use it for many things, but we cannot implement a qubit with this, as we were saying, because the spacing between the 0 and 1 states is the same as the spacings between all of the other frequencies. So something you would want to have is that the spacings, so this spacing is determined by the curvature of your potential, and for a parabola it's the same everywhere. So something that you would want to have is that the curvature of your potential changes at higher energies, so that the spacing between these frequencies is not the same everywhere. And we are very lucky to have something called a Josephson junction, which does exactly that, right? So a Josephson junction consists of 2 superconductors that sandwich between them an oxide barrier. So there is a phase drop phi across them, a superconducting phase. In reality, they could look something like this, although there are lots of different designs for implementing them. And if you look at the response of the relation between inductance, phase, and current through them, you see that they behave almost the same as an inductor. So there is some relation between the inductance and the current, but instead of it being linear in phase, such as for a linear inductor, it's now taking the shape of a cosine. If you write down this like effective potential energy term in the Hamiltonian, instead of it being quadratic like before, it takes the shape of a cosine. So we can take our resonator, remove the inductor, and we had a black Josephson junction there to create a transmon qubit. Just before showing that, to see how that looks like, so this is again the chip that we were showing before with all of our resonators around them. And one way of implementing one transmon would be putting these 2 squares. These are 2 metallic plates with some capacitance between them, and in between both, putting your Josephson junction. So yeah, and this is just the exact analogy to how the resonator looked like. So we replace the inductor by the junction. What do we have? We end up having the same Hamiltonian as before with the capacitive part before, and then we have this cosine term that comes from the inductance. Now, instead of having a perfect parabola, we have this cosinusoidal shape, and I'm showing only one period of it. You can go and expand your cosine as its Taylor series, and it's actually quite parabolic, close to 0. So this first term is really exactly the same thing that we had for the inductor, which means that in this bottom region of the potential, it is the exact same thing, or almost. The first order is the same thing as the resonator that we had before, which means that if you diagonalize your Hamiltonian, you end up getting these two eigenenergies with a certain space in between them that have a character very similar to those states that we had before in the resonator. If you keep finding higher and higher states, though, you see that they, because of this reduced curvature of your potential, they will be less spaced from each other, which is exactly what we wanted, because if now we send a drive to our transmon, so if it starts in the ground state and we send a drive, it will start exchanging oscillations between the 0 and 1. So this is what we call Rabi oscillations. This excitation moves up and down without leaking out of this 1-0 computational space. So, I mean, of course, if you do this not carefully enough, and instead of and you also have a tiny bit of a component in your drive that is at the frequency of the 1 to 2 transition, you could leak out. So this has to be done quite carefully. But in principle, it's possible to manipulate your system so that you stay always in the eigenspace of 0 and 1. And this is what we do. Just to see a bit more in detail how this, so you would think this system is actually quite simple in that there's two free parameters, right? It's C and EJ. So there cannot be so much going on. It actually depends quite heavily on the values of these parameters, and it behaves very differently depending on different regimes. In the regime of large EJ over EC, so EJ is very large compared to EC, you have that if you again write your Hamiltonian in the ladder operator basis, which now is not the eigenbasis of the system anymore. It's very close to being the eigenbasis for the low part. So you end up having this term coming from like the quadratic part, same as before, which determines the space in between 0 and 1, so this energy. And then some higher order corrections in terms of alpha, and alpha is what we call the enharmonicity. This determines the difference between the 0 and 1 transition frequency and the transition to higher energy states. So you wouldn't want alpha to be very, very tiny, because otherwise you end up having, again, this problem that you, while manipulating the qubit transition, you might end up going up. And how do these eigenenergies depend on the EJ over EC ratio? You see, for instance, here in A that for small EJ over EC ratios, they depend quite drastically on it. This is something that you don't want. Here, the x-axis is the offset charge in your system. So it's whatever like noisy charges that you have around, whatever voltage noise that comes into your system. This will unavoidably wiggle a bit the x-axis around. If you have that happen, you want your system to not be sensitive to that. So you would want everything to be flat as a function of the offset charge. And if you see here for the top plot, that's definitely not the case. So that's not somewhere where we would want to operate, because otherwise the transmon, or in this case the charge qubit, would be very sensitive to charge noise and would dephase very quickly and lose its state very quickly, its information. What we do in reality is actually going more towards the high EJ over EC ratio with transmons, even beyond 50 that's shown here. I think people would typically stay between 50 and 100, something like that. You don't want to keep going higher and higher and higher, because if you want to keep your resonance frequency at a reasonable range, going to higher EJ over EC ratios means that you have to reduce your EC. And EC happens to be what determines alpha mostly. So if you have very tiny EC, you will have very tiny alpha, so very tiny enharmonicity, and you also don't want that. So there is like this balance, and people would typically converge to something between 50 and 100. So this is how we operate, or how we define these qubits. Now, just to go back to this comment that I made at the beginning about why do we need so tiny temperatures to operate this. This space between 0 and 1 is the computational space, as we were saying, and we want the qubit to always live there. We don't want it to live in any other higher states. We don't want it to be excited. let's say we have our qubit at 5 gigahertz, for instance. If we plot the Maxwell-Boltzmann distribution, so the expected populations that we would have at that energy, both at the energy of state 1 and state 2, we see a qubit excited state population that depends quite drastically on temperature. And if we would, let's say, operate at 80 millikelvin, we would have close to 1%, or close to actually 10% population in the one state, which in the end is not the end of the world because it's still a computational state, so we can control it. But we would also have more than 1 per mil population in the second cited state. So if you look at this line, it's actually quite high up. In reality, especially in the context of quantum error correction, we want this to be much lower than that. So we would want to be towards the bottom part of this graph, which means that we also want to be towards the left part of this graph. And this is what requires us to operate at temperatures of the order of millikelvin. And that's why we use these cryogenic systems that go down to the order of 10 millikelvin to operate at that frequency. This is really, otherwise we would automatically have leakage of much higher level. So now we change gears a bit from the basics of the Hamiltonian of a transmon to how do we read it out. And disclaimer here, we will combine everything that's come until now, like the transmon with the resonator. So I hope you got that first part. This is first more in general. What do we need for readout in general for any platform? So we need our readout to have high assignment fidelity. Assignment fidelity describes the fact that if we have our qubit in a quantum state 0, we would want to measure it, keep it in 0, and obtain a result of 0. If we have a quantum state of 1, we would want to measure an outcome of 1. And if you have some superposition, you would want, with the corresponding probabilities, to either measure 0 or 1. The assignment fidelity measures exactly that. So it's the sum of the probabilities of measuring 0 conditioned that the qubit was in state 0, plus measuring 1 conditioned that the qubit was in state 1. So we want this to be high. Otherwise, what are we doing? Also, in the context of quantum error correction, we want readout to be fast. I mean, in general, we want readout to be fast compared to the coherence times of our qubit, at least, because otherwise you might end up decaying during the process, and you might end up having some errors. But also, if you want to have cycles of measurements and you want to keep measuring over and over time, you want to do this at a fast rate. Otherwise, you also lose information between cycles. And finally, if you have mid-circuit measurements, for instance, or in some situations, you also want to, as we were saying, measure quickly once more after your measurement. So whatever you are using as a detector after the measurements should also go back quickly to its original state pre-measurement to be ready for the next one. In some contexts, you would also want your measurement to be quantum non-demolition. What do people mean by quantum non-demolition? This is basically the transition from the second to the third column. If you have a measurement outcome of 0, so if you've collapsed your system to a 0 during readout, you want your qubit to stay at that state afterwards to continue your computation. So this is what QND means, and this implies lots of different things, such as not having decay during measurement. If you've measured a 1, but then it decays to 0, then you don't have QND. It also requires absence of leakage during measurement. If you, by mistake, excite your readout system a lot while trying to measure and end up sending energy that leaks out your qubit out of the computational space, that's also non-QND. And in general, in the context of having many qubits, you wouldn't want to affect other qubits while reading out one of them. So this is also a requirement. And of course, like always, if you want to scale up, whatever choice that you make should be scalable. So you should be able to repeat it, potentially do some multiplexing so that you reuse lines and so on. So how do we do this in particular in the area of superconducting qubits? There are lots of different ways of doing this. Definitely the most established one and the thing that people do the most is dispersive readout, which is done with the circuit shown here. If you're interested in this topic, I really recommend that you take a look at the literature, because lately there have been quite a few different proposals of how to engineer a bit differently the coupling between this transmon that we have here and the readout resonator, which the most simple scenario is having a capacitor, but you can do other things to actually like end up having other characteristics of your readout, which sometimes can be advantageous. But here we'll just describe this dispersive readout, which is a bit like it's the most established technique that we have. So we go and take the transmon qubit that we had before and the resonator and connect them with a capacitor. So we already had the Hamiltonian of the transmon, we had the Hamiltonian of the resonator, and now we end up having this extra energy coming from the coupling between the two across the capacitor. And the dominant term, or not the dominant, the only term in that interaction that couples the two degrees of freedom of the two elements is this capacitance times the voltage on one node times the voltage on the other. These two voltages on the two nodes of the transmon and the resonator are directly related to their lowering and raising ladder operators that we saw before, so we can rewrite them in terms of that. And typically, we would do this, at least in a scalable regime. We would do this in a regime where the coupling energy between the two objects is much smaller than the self-resonance frequency of each of them, which means that we can also apply what's called the rotating wave approximation and write down this interaction Hamiltonian, rewrite it to first order in G divided by the sum of the frequencies. And if you do that, you end up getting the Jaynes-Cummings Hamiltonian, which looks like that. So the first two terms are the frequencies of the Hamiltonians of the qubit in isolation, of the resonator in isolation, and this last part is the coupling. Now, if you inspect that last part a bit more, it's actually not yet looking exactly as one would wish. So remember this lowering and raising operator, this ACE. What they do is that if you have an excitation, they either lower it, so reduce the number, or increase it. So if you look at the last term there at the end, A dagger R, AQ, what that term does is that if you have your qubit in state 1, it first lowers the state of the qubit to 0 and raises the state of your resonator, which means you had an excitation in your qubit that ended up being in your resonator. Your qubit is where you want your information to be. So if it ends up being in the resonator, that's a problem. That's like information that's lost, especially because we would couple this resonator to the external world to be able to access it. So you don't want these terms in the Hamiltonian that exchange energy between the qubit and the resonator. If you have that, then that's a problem. We have it, so that's unavoidable. But what we can do is detune in frequency these two objects. So for the example that I'll show here, it will actually be with a negative detuning, so that with the resonator at higher frequency than the qubit. And you want that detuning to be much larger than the coupling G between the two objects. If you do that, this is what's called the dispersive regime, or the dispersive approximation. So it's going to first order in that G over delta. And this is what one would typically do in dispersive regime. It's really the title. So if you do that, you end up having that your coupling term now changes shape, and it looks like this 2 chi times the number operator in the qubit times the number operator in the resonator. And this depends directly on G and delta. If we inspect that, this is just writing the exact same thing in the corner. If you highlight the parts that depend on only the qubit, which is this green part, and the parts that depend on only the resonator, you see that the prefactor of the number operator of the resonator, so the prefactor of the orange boxes, has some frequency of the resonator, plus a term that depends on the state of the qubit. So this A dagger A can be 0 if the qubit is in the ground state, or it can be 1 if the qubit is in the excited state. So we would have either FR if the qubit is in the ground state, or FR plus 2 chi in the other case. So that's already nice, because we have something that will be different. We'll have a different resonance frequency depending on the state of the qubit, and this is basically what we wanted. So now you can go and connect a probe, a drive line, and send a probe through it, something that allows you to send an excitation to your resonator, and also connect an output line with a certain coupling capacitance to it, and see what comes out. If you do that, and you measure the transmission of your the amplitude of your transmission signal. If the qubit is in the 0 state, then your resonator resonates at that FR frequency, and you see some peak in transmission. And this kappa, which is the line width of the transmission through the resonator, depends directly on your coupling capacitance, CK. If the qubit instead is in the 1 state, we were saying the resonator frequency changes. Now, this 2chi in this particular case is negative because I'm assuming that the resonator is above the qubit. If it was the opposite, it would be the opposite. So if the qubit is in the 1 state, you see a peak at a different position. This is the amplitude of a transmitted signal. If you choose to instead look at the phase, you see that also in the region around these resonance frequencies, there is like a very different signal in phase between one and the other. So this is just so that you're also aware it looks like they're at the exact same center between, the two peaks. Maybe in amplitude it looks like the signal would be minimal, but if you look at phase, it's actually maximal for phase there. So this is what we would want to detect experimentally. We want to probe this resonator to have at some particular chosen frequency, to have information about whether the qubit is, whether the resonator is in the purple or blue line, so that makes us learn about the qubit. And the way in which this is done in practice experimentally is that you would go and put your transmon and resonator inside a cryostat with a line arriving to them and another one that you will use for readout. And you can generate some signal at a certain oscillating frequency, up-convert it, send it through your attenuated lines in the fridge. Then maybe in the output you have a bunch of amplifiers, some quantum-limited amplifiers at low temperature, some isolators. And then you end up getting your signal, down-converting it again to lower frequency, and see what you get. So if, for instance, you send a pulse with a certain duration and some oscillatory frequency, and look at what comes out, you will end up having, there is always some ring up and ring down time coming from the fact that this resonator has a certain line width, so it takes some time to get excitations into it and out. But then also there is a component with a prefactor I that is in phase with whatever you put in, and some other component that is out of phase, precisely. So you can take out these I and Q values and plot them in some 2D plane. And you end up getting 1 point if your qubit was in state 1 and another point if it was in state 0. Depending on what exact frequency in the x-axis you choose to read out at, you would be somewhere else in this circle. But yeah, for instance, here, if you read out at that orange tick, you would be maximally split in quadrature and wouldn't have any signal in phase. That's what we were saying there. So this would be ideal. You just do this and get a point. In real life, there is noise, though. So some of this noise might be coming from thermal noise from your amplifiers, for instance. But some of this noise is actually unavoidable because it's quantum noise, so it's the limit, the minimum limit you can have. So in real life, whatever you do, whatever optimal your setup is, you end up having that if you repeat this experiment a bunch of times, instead of getting this fantastically isolated 2 dots, you instead have a blob of probability around those ideal points. You can, and I think I failed to mention that, the best situation to do so is to measure with kappa equals to 2chi. So when the line width of the peaks is the same as the separation between the peaks. So I'm plotting here the situation in which you choose to do that. So the SNR, meaning the signal-to-noise ratio of your measurement, is just the distance between the centers of the peaks divided by their the centers of the blobs divided by the variance around them, the spatial distribution. And you can, we described earlier the estimation fidelity. You can rewrite your estimation fidelity as a function of the SNR, and in turn as a function of a few relevant parameters in your circuit that determine it. This is in the ideal scenario where you don't have any preparation errors in the system, where there is no T1 decay or anything like that. Really, in an ideal scenario, you would have that your estimation fidelity depends on a few different quantities that, in principle, you can tune to play with that. So one of them is the TM, the total measurement time. Just to have some intuition about that, if you plot your 2 IQ plane blobs as a function of the measurement time, their spacing between the centers scales linearly with time, and the size of the blobs scales as the square root of time, and that's why we end up having a dependence of the SNR on the measurement time that goes as the square root. Apart from that, you can have you have these other parameters that you can, in principle, if you want to increase your estimation fidelity, you can increase. One of them we just mentioned, and in principle, you can make it longer, but as we said before, you have to be careful with the relaxation time, and also with how much signal you put into your system. That is not going to heat up. And in the situation in which you want to do this in cycles, so you want to do some repeated measurements, you wouldn't want to make your measurement time super long otherwise, and everything ends up taking too long. Something else you can increase is your quantum efficiency, but this is, you would typically just maximize that. It's like the amount of, it measures the amount of noise that your readout chain introduces unwantedly into the system, so this would be just maximized. And something else that you can do is increase these kappa and chi parameters. Just as a reminder, chi is determined by the coupling capacitance between the qubit and the resonator. That's for chi. And kappa is determined by the coupling capacitance between the resonator and your output line. So if you increase both of them, you also end up increasing in total the coupling between your qubit through the resonator to the readout line, and you might end up having some decay of excitation through that path. That's what we call Purcell decay, and you don't want that to happen, so this is something you want to be careful with. Qubit dephasing can also be a problem if you start increasing chi a lot. So you remember chi determined how much your resonator shifts if you excite the qubit. This Hamiltonian was fully symmetric, so it also determines how much your qubit shifts if you excite the resonator. And if you excite it a lot, it will shift that times the number of excitations. So this parameter chi measures that effect, so you don't want to excite your resonator a lot, otherwise you end up having qubit dephasing. We also can have readout crosstalk. So imagine you are working on these things at scale. So you might have some band reserved for your qubit frequencies or for like whatever other frequencies you want to deal with. And maybe that restrains a bit what band you have available to place all of your resonators if you are multiplexing them in the same line. So if you increase the kappa, the line width of each resonator, you can have that they start actually overlapping a tiny bit with each other, so they can end up cross-talking with each other. And that would be a problem. And finally, the easy budget on the qubit is again related to the capacitances. So chi was determined by this coupling capacitance between qubit and resonator. Normally, if you are like doing this in a processor where you have a bunch of other qubits and want to couple to them, especially if you have high connectivity, your qubit also has a bunch of other capacitances coming to it that go to like another qubit or whatever. And all of these add up together, so the total capacitance of the qubit can quickly increase. And this is inversely related to the charging energy, which we were saying we want to keep at a reasonable level. If it's too tiny, then an harmonicity is too small, and that's a problem. So we have a minimum charging energy that we want, or like a target charging energy, so we cannot keep increasing like crazy the capacitance for chi, because otherwise it might not be compatible. And finally, about increasing the power, so the number of photons in our resonator that we used to read out to increase the estimation fidelity. You can run into some problems. Qubit dephasing we've mentioned already. And something else that is actually a quite active field of research at the moment is MIST, is measurement-induced state transitions. So you can have that if you put too many photons in your resonator, some of them end up leaking actually towards your transmon at a high energy state. And that would be a problem because that's leakage, and we never want leakage. So now in the next couple of slides, we will look in a bit more detail at two of these effects. One of them is Purcell loss, and the first of them is MIST, these measurement-induced state transitions that we were mentioning, to have a bit more intuition of why that happens. This is a characteristic intrinsically of dispersive readout, which comes from this transverse coupling between the two objects that we don't want. And it results in qubit leakage, so let's first get a reminder of what qubit leakage would be. So if you start, you typically would want your leakage to your qubits to be in some superposition of 1 and 0, like here. And maybe you try to do an operation to just send some energy to play within the 0 and 1 state, 0 and 1 manifold, but maybe by mistake you end up sending your qubit up to the second state. This would be leakage. This can also happen without you doing anything, just if you have too high temperature, maybe by itself it goes up in energy. And these two things are things that we would want to avoid, and typically we work so that they don't happen. Another thing that can cause leakage is readout, and this is what these measurement-induced state transitions consist of. So we were saying before that we designed, so now this thing on the left is the qubit. That's why it's bent a bit. This is the resonator that we are using for readout. And we were saying that we designed the resonator and the qubit so that their frequency spacing is different, so that they are detuned, and we work in this dispersive regime. They are detuned for the low energy states, but since the resonator has states that are equally spaced between each other, and the transmon qubit has a spacing that changes with energy, it's quite unavoidable at some point it happens that one particular state of the resonator at high energies is exactly resonant with some particular state of the qubit. And remember, we had this Hamiltonian that exchanged excitations between one and the other. We just went away from that for these low energy states because we detune them and we don't have them in resonance. But if this happens at high energies, that they are perfectly resonant with each other, if you don't have anything in the system, it's still fine. If there is no excitation either on left or right, it's OK. But now if you want to use your resonator to read out and blast it with a lot of energy and excite it to high energy states, it doesn't even look as in this simplified picture. You would actually have a Poissonian distribution of excitation. So it's not that you can choose, yeah, but I only excite it to the state 2 or 4 or whatever that's not resonant. It will be unavoidably in many of the states. You end up having that because of this transverse coupling, you can leak. And if your qubit is in any state that is not in the computational manifold, it's already a problem because that's leakage. So this is the problem that one of the challenges that dispersive readout can run into. And actually, it's quite complex because it really depends on all the quantities in your Hamiltonian. So it depends on the qubit frequency, on the resonator frequency, on the enharmonicity, which determines how this spacing becomes smaller and smaller as you go up. Also on the average resonator photon number, so where in this spectrum you put your excitations, and even on the charge dispersion and charge offset that you have in your transmon. So you remember that we work at some regime for which the transmon bands are perfectly flat in offset charge. This happens for low energies, but the very high up ones actually still remain having some relevant charge dispersion, so that even maximizes a bit more the probability of having these transitions. So if you're interested in this topic, there is plenty of work that's available of very recent experiments and theory investigations that people have done in the past, and they are all really interesting, and this is advancing super quickly, investigation of this effect. You see here one example where we are plotting the probability of leakage, so the more black it is, or the more blue, the worse, as a function of the photon number and the detuning between the resonator and qubit. And you see that even for quite low photon numbers, you will encounter some detunings where this happens. And if you are thinking in scale, you have to be really, really careful designing your system so that you don't have these problems. And typically, always measuring with a lower photon number would help. So this is for one of the two challenges that we were mentioning with readout. The other one was Purcell decay, where, as I mentioned before, it's like losing your qubit excitation into your readout line. So something that you could do, which would be terrible, would be to directly couple your qubit to the readout line to readout, for instance. If you do that, first your measurement wouldn't be quantum non-demolition, so it would already be a problem. But apart from that, you have some transmission between the qubit and the readout. And if you translate, and that ends up making, with a certain rate, losing your excitation from the qubit. So if you translate that into a T1 time, you would end up having a T1 of a few tenths of nanoseconds, which you don't want. So this is a no-go for so many different reasons. The alternative is standard dispersive readout, what we saw. You put a resonator between your qubit and your readout line. If you do that, this resonator acts as a filter that makes this transmission between qubit and readout much lower at the chosen frequency band here, the red one for the qubit, which ends up resulting on a T1 of your qubit that is already quite a bit higher than before, but it's still, for this parameter set, limited to a few, maybe tens of microseconds. So that's still not enough if you want to scale up. So something that people have done also is coming up with this concept of a Purcell filter, where you add something else that keeps filtering the path between your qubit and your resonator and your readout line. So something that you can do, maybe the most simple approach to this would be adding one more resonator in series, where these two resonators that are perfectly resonant with each other hybridized result on two different transmission peaks, and the transmission at your qubit band in the end is much lower. So this results on a T1 that's much higher, and instead of having a T1 that went as the square of your tuning in the previous case, now it goes as the power of 4. So this really brings up T1 by a lot, up to above milliseconds, which is already quite good. If you want to bring it up even more, you can Purcell filter even more. And there are you can come up with a bunch of ways of doing that, right? You can keep adding modes that filter in your readout chain. One of these options is shown here as an example, where you would add one inductor, one extra inductor in parallel to that capacitor there. In this situation, apart from having your band pass modes that you had before at the resonator frequency, you also have a band stop mode at the qubit, or you can design it so that it's at the qubit, of course. And this will even protect the T1 of your qubit even more in the band of interest. Of course, it doesn't mean that if you build this circuit, you will then have a T1 of a bunch of seconds, right? This is the Purcell limit to T1, but you might still have in your chip some other sources of noise or something that could limit it further. But at least you make sure that you don't lose your photons to the readout line. I still have two quick topics before we turn to part 2. I don't know how we are doing on time. Maybe I go quickly through this so that we have some time for part 2 later. And so if you have any questions about these two topics, I will just mention them very quickly, and then we can discuss them later. In this way, we can have a short break between part 1 and part 2. So I'll just show you the images very quickly, and then we discuss them later whenever you have time, so that we have a bit more time for the second part. Basically, for single qubit control, something that you can do is sending one pulse through your drive line at the qubit frequency. This comes into the Hamiltonian as this time-dependent term that makes your qubit oscillate between the 0 and 1 state. And this is what we call Rabi oscillation. Depending on the phase of your drive signal, this term there at the end, you end up having that these Rabi oscillations happen around one axis or another in the Bloch sphere. So you see in this example here that if you drive with a phase of 0, you would rotate around the x-axis in the Bloch sphere. So this is an x gate. If you do it with a phase of pi, you would rotate around of pi half, I guess. You could rotate around the y-axis. And if you want to rotate around the z-axis, then you can actually do this with a frame of reference. You don't even have to send a pulse. This can be a virtual rotation, just changing the frame of reference of your qubit. So this is how you do single qubit gates. It's not you just drive your qubit. There is some more subtlety to it, but just don't want to spend a lot of time on it for the sake of time. In reality, there are a lot of different ways you can choose to send your drives through different lines for qubit and resonator, but something that you can do if you want to reuse lines is send your qubit pulses to implement the single qubit gates through one line, combine them to your readout line, and simply apply how much power you need for your qubit so that your qubit signal goes through the resonator and makes it. If you want to apply different single qubit gates, such as the Hadamard and the Y gate, you will choose your rotation axis for each of them by changing a tiny bit the phase of your input tone, and the angle of rotation for each of them you change by changing the amplitude, for instance, of your pulse. So this would be one example of how you can make, if you go in your computer, write your quantum algorithm with some gates, the actual pulses that go into the system would look like something like this. This is for single qubit gates. 2 qubit gates are quite a bit more complex, because now instead of having 1 qubit with 2 states, we have 2 qubits with a total of 4 states. So 2 qubit gate matrices look something like the one shown here. A C0 gate is is a controlled knot. So based on the state of a control qubit, your target qubit receives or not an X rotation. So that's why here you see, if you look at this bottom block of this CNOT gate, it looks exactly like the X rotation. A controlled C gate is the same thing. You have or not a C rotation in your target qubit, which is this block here, depending on whether the control qubit is in the 0 or 1 state. So this is something that there are many ways of there are many approaches for implementing this experimentally. One way would be, for instance, having tunable qubits. So if you have tunable qubits, so you can move their frequencies up and down. You can make your qubit frequencies be close to resonances at high levels, like maybe your 1-1 state, where both qubits are excited, comes close to resonance with the second excited state of some of the two qubits and picks up some conditional phase. Some alternative would be to have two qubits partially coupled to each other and send a resonant tone to one of them that's resonant with the frequency of the other. And something else that people do is using tunable couplers that I want to show here. And let's not go through the math in detail because it can be quite dense. But basically, you have something in between that you can tune. And you can basically have a Hamiltonian with your single bare Hamiltonian of each of the two qubits, and this coupling term that determines the coupling between the two of them. For this particular case that I showed here, you end up having that the transition frequency of one qubit depends on the state of the other qubit. So you see that for qubit 1, for instance, you can have either a minus sign contribution or a plus sign contribution, depending on the state of qubit 1. And this ends up making that if you activate your tunable coupler for a bit, for some certain amount of time, depending on what state in the two-qubit state you had, either 0, 0, 0, 1, 1, 0, or 1, 1, it will over time pick up a certain phase. These certain phases are actually rotations on the target qubit. So let's say these submetrics correspond to the target qubit, depending on the control being in 0 or the control being in 1. There are rotations in the block around the C-axis that are conditioned on the state of the control qubit. And this is already very similar to what we want for a controlled C gate, right? It's a rotation around the C-axis that's controlled based on the state of the other qubit. It's just looking a bit different because of the directions. So this one can fix by first choosing what actual angle of rotation you want, so just activating this coupling for a concrete amount of time. And then applying single qubit rotation. So in particular, in this case, you have to apply the square root of a C rotation, so this kind of matrix to both qubits. And then you end up having that you recover from this interaction with the tunable coupler, you end up reaching your control C gate. So the way in which this happens is you apply it once, which flips the sign of the second and fourth terms. So you end up having 1, 1, I minus I, and then you apply it on the other qubit, and you flip and you multiply by I the bottom block, so you have 1, 1, 1, minus 1, and then you're done. So I know this goes very fast, but just let's discuss it later in more detail if you are interested. And just to get ready for the second part, I want to mention that we always have errors in our system, so it's unavoidable to have some decay, some decoherence, some gate is not perfect. So people have come up with a bunch of ways of dealing with these errors, such as, for instance, echoing during idle time, so sending some pi pulses that make your slow noise cancel itself over time if it's not evolving very quickly. You can also do quantum error. Like you can also detect errors and try to correct them classically, or do any type of classical post-processing that attenuates the effect of errors. And finally, you can also do quantum error correction, which is what will come now back in part 2, which consists of taking several physical qubits to combining them and encode the state of one logical qubit. So now I think you guys deserve a short break if you want to go to the bathroom or something for a moment. But we should be back quickly so that in the next few, like, I don't know, 25 minutes or something that we have left, and we go through this part to see how this will be more in particular how the example of how IBM is going towards fault tolerance. So let's take a short break. And if you have any questions now during this couple of minutes then about part one, then it's also a good moment to ask them. Oh, sorry, there's this.
Okay. Can you hear me?
Yeah.
I was wondering if I understood correctly, you showed that the initial state that you have, so how polarized it is, depends exactly on the temperature at which the qubit is, right?
Okay, let's see how long it takes to go back.
So the population, there's in
So
one,
not the exact
two...
state, but the probability of it being in one or the other, right? Okay, I shouldn't have done this. There are way too many slides to go back. Here. So I think this is what you were referring to, probably.
Yes, exactly.
Yeah.
So I was wondering if in this community, is it possible to dynamically cool down the qubit farther than the temperature at which it actually is?
So that's close to what we call conditional reset, for instance, or reset in general. If you have some population in your one state and the lifetime of your qubit is long enough, you can measure it, know that it's in the one state, apply a pi pulse, and bring it down to the ground state, for instance. The problem is if you end up having high populations in high energy states for which for each of them the transition frequency that you would need to go to the ground state is different. It would actually be quite challenging. So it depends on what type of populations you have. For excitations to high energy levels, we will actually see in part two, you can use like some other constructions of reset gadgets that allow you to reset unconditionally everything above. But you would need some source of coldness in your system. Yeah.
Thanks.
Hi, thank you for the talk. So far you described leakage like something bad, something to avoid, right? But since you can create leakage by operating your qubit, so I can imagine you can engineer leakage to use it, for instance, to just build an artificial environment and then with a special spectral density and then check or play with open quantum systems. Yeah.
Yeah,
So,
I guess in that situation it would be a good thing. I consider it bad in general if you want to do like quantum error correction, for instance. But yeah, you can gain information, I guess, about like you can use it for physics experiments, right? That's what you.
Yeah,
is
exactly.
it what you are referring to? Yeah.
Yes, exactly. And I mean, I'm not an expert, but I've known that some gates are operated through leakage, through engineer leakage. Right?
Yeah, well, actually, that's true, and that you have to be very careful with them also. So for some 2-qubit gates. That I think is mostly if you have tunable qubits. So for instance, you have 2 qubits and you bring their frequencies to a position so that the 1-1 state, so this basically the sum of the qubits of both, the frequency of both qubits is very close to the 0-2 state. So this is a leakage state. And then you have some extra pickup phase, some phase that you pick up because you end up oscillating between the 1-1 and 0-2 state. But then you have to be very careful that you don't end up by mistake in the 2 states. So, but yes, you can leverage that to do a 2-qubit gate, for instance.
Thanks.
If there's no more questions, let's go for the short break, and then we go back in 5-8 minutes, okay?
Let's go. Right, here we go now. Batman scoop on the mic, mixing the mix on the wheels of steel. This is what I was fucking born to do. Let's go.
Esto funciona, perfecto. Vale, pues ahora vamos a seguir con la segunda parte, un poquito más corta que la anterior y también prometo que con un poquito... Ay, perdón, inglés. So we'll continue with the second part, a tiny bit shorter than the previous one, and I also promise there will be a tiny bit less math than before and more photos. So as I was saying at the beginning, this second part is on seeing how to approach fault tolerance in the coming future, so how to implement a quantum error-corrected system at scale. And in particular, I'll go through the approach that IBM is taking to do so as an example. So we start with a very dense slide, and I apologize for that, which is the IBM roadmaps towards fault tolerance, which looks something like this. And I'm sure many of you might have seen it already before in the website, for instance. So since 2020, IBM has been tracking its progress towards fault tolerance with this roadmap, where you see here in the x-axis the time, both past, present, and future. And the different rows show developments in different areas, such as algorithms, applications, software, integration with high-performance computing. And in particular, I'm highlighting the part that's related to hardware, because that's what I work on and what we can discuss here in more detail. Everything that is like a bit more hidden is progress that's happening in parallel, but many other excellent teams inside IBM that are working in these topics. So within hardware, you see two different blocks. The top one is the development roadmap. The bottom one is the innovation roadmap. So the development roadmap is composed of sub-blocks. Each of these is like a different quantum chiplet or quantum processor. They all have bird names. And these are the devices that are made with technology that is very well under control. They're fabricated and they are deployed, so they are accessible by clients or external users. So they are like quantum processors that are put in the cloud and can be used externally. The bird names in the innovation roadmap are mostly internally deployed towards internal research at IBM, and they are used to develop some particular types of technology. So they're a bit more targeted and more concrete, and it's typically technology that that will be needed later on in the roadmap in the development part. So for instance, Loon, this latest device in the innovation roadmap, was one particular quantum chip where IBM developed C couplers, which are long-range couplers between two transmons in the same chip that are coupled to each other over a long distance. And these will be needed later on towards the fault tolerance, the last part here of the development roadmap. If you focus now on the development part of the roadmap, you see, for instance, that for the next few years, we have a different series of generation of improved Nighthawk devices. Nighthawk devices are quite different from the devices that came a bit earlier in the roadmap and that are still available in the cloud. So for instance, before we had Heron devices and some other types of devices that had this heavy hex connectivity between qubits. So each qubit in the grid would be connected maximally to 3 other qubits and sometimes even to 2. And this would make a somewhat sparser grid of connectivity. Nighthawk has a square connectivity, meaning that each qubit is connected to 4 other qubits in the grid, so it's a square lattice. And this allows the users that run their algorithms there to do so in a much more efficient way. So in the end, you need less gates to end up implementing the algorithm that you want because of the increased connectivity. These together with error mitigation techniques. So you see here, it's maybe hard to see from the distance in these gray blobs. It says error mitigation. So these are devices that are using very heavily error mitigation, but they are not yet quantum error corrected. This combination of high density and error mitigation allows actually to reach very high number of total gates that can be done in a circuit. So for instance, this is the name that you see in brackets there. And this is in the end what users care about the most. If you want to run your algorithm in a quantum processor, you want to be able to do many gates. In the end, this is the main metric that has an impact on the circuits that can be used, that can be run. And this is a quantity that, thanks to error mitigation, will be readily increasing, and thanks to the improved technology in these Nighthawk devices, will be improving in the next few years. And it's anticipated that this will enable, already before quantum error correction, that this will enable quantum advantage with these devices. What comes next is a paradigm change. It's completely different. These Starling and Blue Jay devices are already fault tolerant, meaning that we have quantum error correction here. We don't have just physical qubits anymore. We have logical qubits encoded with many different physical qubits. And this results on a huge increase in the total number of gates that one can run in circuits in these devices. And this is actually coming really soon. So that's why, partially, for instance, some of these devices in the innovation roadmap are actually already implementing parts that are critical for instance, IBM Quantum Starling, which is really coming in 2029. All of these, everything that is here, or most of the things that are here in the past part, many of these devices are put in the cloud, as I was saying, and can be accessed through this IBM Quantum platform, which is available for users, for any user. So basically, any of you can go log into this website and create a profile and go and run an algorithm into one of these quantum processors that are online. There is this list of processors that are already working that tells you how many qubits it has, how many jobs are pending to run, whether it's a Heron, a Nighthawk, what kind of connectivity it has, and some other metrics, such as the 2-qubit gate fidelities and other things. And if you click on one of them, it tells you really a diagram of how is the connectivity grid, and you can really think exactly what qubit you want to use for your algorithms with what T1 and so on. And these metrics are updated over time because things evolve, so you can check live, okay, what's the median T1 exactly at this moment in this particular processor. The way in which one would do that is writing directly Python code in Qiskit, and let's say you want to implement this circuit, you just write some code quite simply that implements that circuit. And I didn't really point at it, but here is also a list of native gates for each of these different devices. And it might be that some of the gates that you choose as a user are not in that list, such as, for instance, let's say this C0 gate, this control NOT gate, is not a gate that's natively implementable in one particular quantum processor. There's another step, that's the transpiler, that transforms this circuit into another series of gates, such as, for instance, in this case, the 2-qubit gate involves is a control C gate instead, that is already readily runnable into your chosen quantum processor. This step here, where it says target equals backend, the backend is what chip you want to run it on. So you first choose one, and then the system transpiles your circuit. And finally, you send your algorithm, you run it, your job, into the quantum computer. You have to specify a number of counts, which is how many times you want to repeat it for statistics. You receive back the data, and this is something that can be then processed to extract information. Of course, this circuit that I put here is like a super minimal, simple circuit, but I want to highlight that these processors that are already available have been used by plenty of researchers at really high, for high-end publications with more than 100 qubit devices in a lot of different areas of research. Many of them not even necessarily related to quantum computing. So many of these publications are actually using quantum computers already as a tool to investigate things in the areas of quantum, of material sciences, or RNA or different things. Some of them are more related to quantum computing, some are in different domains, but it's really showing that this is already being used as a tool by very high-profile researchers. So this is very encouraging. And now, before switching to a more technical part, I just wanted to show you how these quantum computers actually look like, the ones that we have at the moment. Some of these are placed in data centers of IBM. One of these is in Poughkeepsie in the US. The other one is in Germany, in Anningen. So for instance, I think this image from the black one is from Anningen. And some of these quantum computers are placed directly at client locations. So at like some hubs where there is like a lot of community or a community of quantum researchers that decide to have their own quantum computer in place. This is what happens, for instance, for some of the IBM System 2s. So the ones that are around like this are System 1s. The second generation is System 2, which looks more like that one there. And interestingly, this System 2, there is one in Poughkeepsie, in the data center of IBM. There is one in Japan, and the only one that exists in Europe is actually in San Sebastian. So one of the only 3 System 2s that we have is here in Spain. So that's the more like shiny part. Now I want to see to explain you what enabled until now this technology. This was enabled by lots of advancements also in the control electronics, the wiring, like how you bring your signals into the fridge and many other aspects. And one of the things that I like to discuss is the packaging. So how do you make your actual quantum processor? So one can think of a first generation, and we'll go through 4 generations of packaging. One can think of one of the most simple ways of doing this, which is you take your chip, you place it directly into a PCB, a printed circuit board. You have some pattern layer of metal at the top, this blue stuff, is the pattern metal, and you wire bond it on the edges to your PCB. This is something that, if some of you work as experimentalists in this area, you might have done in the lab, actually, in an academic lab. This actually works quite reliably, and one of the issues is that it limits your topology to like a ring topology. So you end up having to have your wiring readout resonators and any other elements going towards the outside world because things cannot cross each other. So unfortunately, we don't want to build our quantum computers as rings, and that's why a first step was to move to generation 2, which is this flip chip technology, where now instead of one wafer, you have 2. The qubit wafer and the interposer wafer, and these are connected to each other via superconducting bumps. Then something that one could do would be, for instance, putting their qubits on the qubit wafer and their wiring for control and readout and so on the interposer wafer. And this is shown in the diagram with blue for the qubits, for instance, and then red on the interposer for like readout wiring and control. This allows to cross lines already. So you can have that your readout wiring can reach the center part of the chip. So you are not limited to a ring anymore. You are limited to a planar grid. And maybe the only disadvantages of this would be that you might have, or the main disadvantages, I would say, are that you could have crosstalk through this gap between one red line that crosses a blue line, because there's just vacuum in between them. And also that in the end, you reach your periphery of the interposer wafer, which is like a linear periphery, and then you are limited by that space to put wire bonds on the side. So in the end, this limits a bit also your wiring that you can route out. That's what motivates the development of generation 3 of packaging, which incorporates this multi-level wiring technology, which is this part that you see here as MLW. So it still has this qubit wafer and interposer wafer, but then this interposer wafer, apart from having the patterning, can have some through substrate vias, these TSVs that go to some multi-layer wiring that isolates this control readout and whatever wiring that you want to put there, both from each other, so you can have different routing layers here that are isolated from each other, but you also isolate it from the qubit wafer. And also you can have different TSVs that go up to your external wiring, so you are not anymore limited by this perimeter of the interposer wafer. And this allows much more clean and wiring of your control, and it allows to implement much more advanced designs that are not readily available otherwise. So this is something that in a small-scale academic group would be super difficult to do. And this is enabled by having a huge team working on packaging and these fab line facilities that do this fabrication. So this looks already like a lot, but it's not everything we need. This still limits your connectivity between qubits to be a planar topology. And we'll see later that for quantum error correction, we actually would like to have long distance or long range couplers between distant qubits. So we would like couplers to cross each other. We don't want just a planar topology, but something much more intricate, such what's shown here. So that's why generation 4 introduces these low loss interconnects, which is this purple part here on the back side of the qubit wafer, which allows you to couple a qubit that's here to one that's far away through this coupler that can cross other couplers. So this enables topologies of connectivity grids that are not planar anymore, and this will be a very strict requirement for quantum error correction in the way that at least IBM is approaching it. So this, just going back to what I showed earlier, actually this last part, this long-range couplers is what we call C-couplers, which is what was enabled and demonstrated in the Loon chip last year that will be later on used for fault tolerance. So why do we need these long-range couplers? This is explained in this paper from 2024 that introduces quantum LDPC codes, one of which is the gross code. That's the code for quantum error correction that we are trying to implement. This code requires not only 4-fold planar connectivity for each qubit, so for connections to neighboring qubits, but also for each qubit you need 2 distant connections to other qubits elsewhere on the chip. So that's why we need connections to cross each other, and that's why we need that entire development of the packaging technology to enable that. Why do we want to build this if you've heard there are surface codes that, as their name explains, they're in a surface and they're planar already? So the reason for that is actually quite well explained. This is from the same paper as before, which I really recommend you to look at. This helped me a lot to understand how this, where this advantage comes from. So here in the x-axis, you see your physical error rate. You would want to decrease it as much as possible, so you want to move in this x-axis as much as possible to the left, but you might have some unavoidable physical error rates. If you didn't have it, then you would be done. And depending on what quantum error correction code you choose, which are the different lines, you end up having a different logical error rate. So you want these to be as low as possible in the y-axis, of course. These first plot are different types of quantum LDPC, low-density parity check codes, out of which the black is the one that we are interested in, the one of our choice. And these numbers indicate, the first one, how many physical qubits do you need to implement, the second number of logical qubits, with a distance of the third number. So the distance, the third number tells you how many errors you are resilient to. So you want the first number to be as small as possible, with the other 2 numbers being as large as possible. If you compare these to surface codes, now we are comparing the black one to all of the other surface codes, you see that with the black one, we want to implement 12 logical qubits with a distance of 12. And if you check which surface code you would have to choose for that, would be, for instance, at least the green one with 12 logical qubits with a distance of 11, for instance. Instead of needing 140 physical qubits, you would need 1,400. So this is a 10x increase of number of physical qubits that you would need to do that. So of course, there is this price to pay of increasing the connectivity, but in exchange, you have to have 10 times less qubits to do so. So this is the motivation for why we are interested in these LDPC codes. This now changes quite radically the connectivity grid. So if you remember, this is the heavy hex lattice that we were mentioning before, for instance, of a Heron chip. For a chip such as Loon, and what will come later for Starling, these quantum error corrected chips, you need this type of connectivity that's shown here at the bottom. So this is quite radically much more heavily connected. So this is enabled by the development of some individual steps that happen in the innovation roadmap that then converge towards Starling, the IBM Quantum Starling, for instance, later on. Some of these requirements are 6-fold connectivity for each qubit, long-range couplers. So these C couplers, each of them have to fulfill all of these requirements. They have to be, it should be possible to connect them, 6 of them to a qubit, to have them long-range, to have these, route them through higher layers so that they can cross each other. And this is not related to couplers specifically, it's about reset, but if you want to do your cycles very quickly. In quantum error correction, you typically would want to reset whatever leakage or initialize your qubits quickly, and for that you need a gadget specifically dedicated to doing so. So here are some experiments that demonstrate each of these requirements from chips that are not as large scale as the ones such as Loon that integrate all of these technologies together, but just demonstrating each of these requirements one by one. So this is a demonstration of a qubit coupled to 6 tunable couplers around it. The numbers in purple are the 2 qubit gate fidelities that are achieved in this chip. And you see that without degrading, while keeping high coherence properties of the qubits, you can get 2 qubit gates infidelities between 3 e to the minus 3 and 5 e to the minus 3. So this doesn't degrade the 2 qubit gate fidelity. Then we also have the requirement of having actually physically long couplers in the chip. You might have a qubit on the right corner of your chip that has to be coupled to another one really far away, so it has to be long. And this comes with several design challenges. It's not so easy to make a structure that's long and doesn't come with unwanted lower frequency resonances, for instance. So this was also something that required quite some development effort and was demonstrated. Here you see, for instance, tunable couplers that range from 6 millimeters up to 18 millimeters long. So this is a really microscopic length scales that, without degrading the single qubit coherence, end up at 2 qubit gate infidelities that range between 1 and 3 e to the minus 3. So same 2 qubit gate infidelities are achieved with like really large tunable couplers, which is a strict requirement for these LDPC codes. Back to these C couplers that are also required. As this is just assuming to what we showed earlier. So they're implemented in these purple C coupler layers in a technology that incorporates also these bumps to connect the 2 wafers to each other, this through substrate vias, this multi-level wiring technology to route out the signals. And in a chip such as this, one goes and implements in the C coupler layers these 2 qubit gates that can cross each other. And now you see here in these percentages the infidelities of these gates that stay in the range of e to the minus 3. So this also has shown to work. And it's really like couplers that go through these different layers up and down and cross each other. So this is really exciting that this is working. And finally, before ending about reset, if we, by mistake, at some point have our qubit during the computation in the 2 state, resetting it would be bringing it down to the ground state. And that's something that you could do by waiting for a certain amount of time so that it naturally decays. But if you have long T1 times, that would require a lot of time. So we have implemented this. I'm going a bit fast because we should finish soon. We have implemented this reset gadget that actually allows you, it's like a switch that connects your qubit to a 50 ohm cold load. So it allows you to either have a very long T1 or a short T1, and you can switch between one and the other with your tunable parameter. Keeping decent T1s at the protect point while ending up with very short and fast decay to the ground state if you switch it to the reset point. This is something that can be done with a reset fidelity of 3 to the minus 5. And in particular, if you test it in a real-life cycle, which is what you would need for quantum error correction, if you don't use your reset gadget over different number of cycles, you can build up leakage population over time. But if you incorporate a reset pulse at the end of each cycle, you can keep that population very low. This part is one of the ones that excites me the most, and this is actually part of the work that we have developed in the team in Zurich that's actually already integrated now in much bigger devices. So with this, I like to show you some images, and we end. This is a comparison of how the Heron chips look like with the heavy hex connectivity compared to Loon with this super entangled connectivity. So you see just by looking at it how the complexity of it went up by a lot. And this is the Poughkeepsie data center in the US that's getting ready to accommodate quantum Starling in just a few years. So this space is already there. It already has some of this IBM quantum system too. This is the one that I mentioned before. We also have one in San Sebastian, this one in the corner. And IBM Quantum Starling will look like this one here. And both the quantum processor part is getting ready, but also the space where it will be put. This is another image of how it would look like. And with this, I know it's been a lot. I would like to thank you for your attention and take any other questions you may have if there is time, otherwise, whenever there is time.
If there's a really quick question, yeah. Please be careful.
Hello. There is an online user that wants to ask you a question.
Yeah.
So Rajesh is asking, what approach does IBM use to do circuit simulation before sending out the layout, etc., for fabrication?
So this is done by a big team using like professional techniques. So of course, it's a very complex problem. Of course, you saw for Loon that you have these intertwined connections, right? And routing them is really complicated to do by hand. So there have been several automatic methods developed internally at IBM that allow you to route all of these lines automatically, leveraging, for instance, classical EDA tools. So these are the tools that are used in classical quantum computing for development of complex chips. Combining that with automation, you can route your lines. This is a strict requirement, especially for like IBM Quantum Starling in the future, that this can be done not by a person routing each of the lines, connecting the qubits one by one, but that it can be designed in an automated way. And indeed, this is also happening in parallel and has been also shown for Loon.
Okay, thank you.
Thanks.
If there is no more questions, let's thank the speaker again, and let's go for the coffee break.
Yep, thanks.
Hola, hola.
just play with you, play with you. Cannot play with you, play with you, play with you. Cannot play with you. Just play with you, play with you. Cannot play with you, play with you, play with you. Cannot play with you, play with you, play with you. Cannot play with you, play with you, play with you. Cannot play with you.
Gracias. Hello. So now we will start with the contribute talks. The first one is Miranda Crow from the Institut de Física Corpuscular de la Universidad of the University of Valencia and of Universidade da Coruña. She will talk about QTYR for physics in LHC. So Miranda, the floor is yours.
Hi. First of all, sorry for my voice. And thank you for giving me the opportunity to talk about our work here in this conference. So QTYR for physics at LHC, where we basically implement a QTYR-based quantum machine learning model for anomaly detection, in this case in terms of high energy physics, in CMS data. So the first question would be, why QTYRs? And I mean, there are some advantages. For example, we have higher storage capacity in front of 1 bit of information per qubit. Also, we have bigger Hilbert spaces, so we have richer set of operations and rotations. And speaking in long term, there are real hardware possibilities. And these four are just a few examples, but there's a lot. And for instance, for some physical systems, for example, neutrinos, it's more natural representations. But of course, there are some challenges, and the first one is the hypersphere, because when you have to work with QTYRs, you have to work with an 8-dimensional hypersphere, and there's no straightforward translation to a quantum circuit. And also, due to geometrical constraints, there's no trivial distinction between pure and mixed states, which is a disadvantage to implement a quantum machine learning model. That's why we spent a lot of time searching for new type of representation within unit spheres, and that's how we found the Majorana QTYR sphere, where we can encode a QTYR pure state using 2 points in the surface of this sphere. So we have, again, a trivial distinction between pure and mixed states, points in the surface are pure states, and points which lies in the inside are mixed states. And there's a straightforward translation to a quantum circuit. So going into details about the Majorana stellar representation. So we have 4 angles. With these 4 angles, we can obtain 2 points in the complex plane, and then doing stereographic projections through the South Pole, we obtain these 2 points in the surface, and we can represent any type of Qt pure state. So with these 4 angles, I'm following, using this formula. I don't have time to explain the derivation. We can encode our Qt state within our quantum circuit. So knowing the basis, our goal is to create a quantum machine learning for anomaly detection, in this case, discrimination between background events and signal events, using Qt. So the first step was choosing a good reference model, okay, a well-established reference model, and use their results for doing a proper benchmarking. So the second thing is to find the generalization of all the qubit-based gates to implement our model. So the first step is, instead of using the Pauli matrices, we have to use the Hellman matrices, which are commonly known in the field of particle physics. And also find the generalization for the rotation gates, which in this case are a combination of Hellman matrices with a normalization factor, and also the generalization of gates like Hadamard gate and the swap gate. So with these generalizations, we can start with the development of our model. In our case, it's a quantum autoencoder model, which is a compressed model. So the goal is to, the model has to learn how to compress a specific type of data into a latent space. So the model learns how to compress this data distribution. So after the training, when you introduce data with the presence of anomalous events, we are going to detect the presence of these events as differences in the performance. Also, speaking about the reference model and the particle encoding, in the reference model, they present a new type of encoding of particle information. They encode 1 particle per qubit. So in their case, they use the azimuthal angle, the pseudo-rapidity, both normalized with the transverse momentum to obtain 2 angles. And using rotation gates, they encode the information of the particle. In our case, as we have 2 more angles, we can try to introduce more information. So we try a lot of different combinations. And in the end, we found that the best performance was obtained when we maintain the 2 first angles as the same as the ones presented in the paper. And the other 2, one possibility is to combine the energy of the jet with a tau ratio. And the other possibility is to use the longitudinal and transversal impact parameters. So speaking about all the process, first of all, we train the model in some cases with real data, and in other cases with simulated data. Then we validate the model using 2,500 events with the same data as in the training. Then we test the model with 10,000 events for each signal, and the same amount for background events to do a proper comparison. And also, at the end, we did the analysis, analyzing the fidelity distributions, the Hawke scores, and some metrics. So speaking about the results, first of all, the fidelity distributions. Okay, this is the fidelity distribution of the qubit-based model, and these 2 are the qubit-based results. So as you can see, I mean, this is a really good result, and it's consistent with the results of the reference paper. But it seems like in the qubit-based results, there's a more clear distinction between the different physical signals. So it seems like the model can detect more subtle difference in the data. So it appears that the QT's model has a greater expressive power. Also, in terms of ROC curves, and speaking about the uncertainty level, as you can perceive, seems like in the Qt-based results, we have less uncertainty, so our model it's more stable. And in terms of Hawke scores, okay, we obtain a comparable performance. Some cases a little higher, some cases it's a little worse, but in most of the cases it's practically the same. Which makes sense because, okay, we introduce more information, we have 2 more angles, but these 2 are phases or are not very significant in terms to create a great difference in the performance in terms of Hawke scores. So going back to the fidelity distributions, as I said, there's a more clear distinction. We use these two metrics to evaluate the distance between the different distributions. We use the Jensen-Shannon distance and the Westersen distance. And in all the cases, for the qubit-based model, we obtain a higher distance between the fidelity distributions. So this proves that we have a higher expressive power. So our model can detect more difference, not only between signal and signal, but also between signal and background. So about our conclusions and takeaways, okay, it seems that the Majorana representation is an effective representation for qubits within unit spheres. We obtain a comparable performance with the qubit-based model in terms of Foucault scores, but always with less uncertainty. Also, in all cases, higher expressive power, greater capacity to discriminate between physical signals, and then we can detect more subtle differences in the data. And we introduce more information in the same number of gates or less gates in some cases. So the only disadvantage here is that we are limited in the computational simulation due to memory consumption constraints. So in the reference model, they use 13 qubits, but we were limited to only 8 qubits. And well, after these results, now we are working on the implementation of qubits to jet flavor tagging. Since now I'm part of the Elite CV collaboration. So we are trying to develop a ternary classification model. Also, we are researching about the QTYR entanglement measurement. And for the future, we have in mind to study higher level systems and also other geometrical representations. So if you are interested in this paper, I really invite you to check our paper. Thank you so much. If you have any doubt, let me know.
So thank you so much, Miranda, for the talk. And now it's time for a quick question.
Hi. Thanks for the talk. Can you elaborate on how does the encoder work?
Yeah, of course. I didn't have enough time to explain this. OK, so as I said, we were limited to only 8 qubits. So we use 4 qubits to encode the information of the particles. OK, so in a quantum autoencoder, we declare, in our case, 3 qubits as trash qubits and 1 qubit in the encoding as latent qubit. So the goal of this model is to move the information from the trash qubits to the latent qubit. And to evaluate this, we declare the same number of trash qubits as reference qubits, initialized to 0, and then we perform a swap test to evaluate how well the model compressed the information into the latent space. Because in the perfect case, all the trash qubits after all the variational process should be at the 0 state. So that's basically how it works.
Thanks.
OK, thanks, Miranda. Now, our next talk is Juan Pablo Uribe Ramirez from the Institute of Física Corpuscular of University of Valencia, and he will talk us about optimized Grover quantum algorithms for querying multi-loop causal configurations using graph theory techniques. So, Juan Pablo, the floor is yours.
Thank you. Well, the introduction has been done, so let's start. OK. First, the motivation of this talk is to use, or of this work, is to utilize quantum computation to do some calculations to applying high energy physics by the great demand that is on computation power to do theoretical analysis or theoretical calculations. Well, what are we trying to do? In this work, particularly, we try to use loop triduality to encode multi-loop scattering amplitudes in quantum circuits. What we're trying to do is to find a way to analyze these kind of configurations of of these diagrams that are equivalent to acyclic graphs, and to find the acyclic configurations. Well, how we do this? Well, a Feynman propagator can be represented as a superposition of propagation in both directions. What we mean is, if we see these arrows, we can set them in different directions, and as a superposition, we can initialize this kind of diagram to represent a direction a particle can travel. Each arrow represents a propagator, or in a simpler way, a particle in the diagram. Okay, so a Feynman diagram is a superposition of 2 to the n states. And the important part about doing this kind of work is to find which configurations are causal, because if we find the particle or our arrow forms a loop, then we have the possibility of having a particle that travels back in time, and that's not allowed by causality. So by this scenario, we say that cyclic configurations are non-physical. So we try to find those that are acyclic configurations or direct acyclic graphs, because these kind of graphs help us to determine which are possible scenarios in physics, or what are actually real. So how we try to do this? We try to do this utilizing the Grover algorithm. It's a pretty known algorithm, but by anyone that doesn't know, we're going to try to represent a little bit. So this is done in 5 stages. The first one is to encode the edge information in qubits. Then we need to initialize each qubit in an homogeneous state. That's done by the Hadamard. Then we need an oracle that represents all the cyclic and acyclic configurations. Then we need to apply the amplitude amplification using the Grover diffuser and measuring the quantum states. So by initializing the qubit in the quantum circuit, we use a superposition utilizing n Hadamard gates in each of the qubits, as is represented. And we need to use a Grover marker or the output and starting in a state. That's done by using the X and the A gate. Then, by designing the oracle, we need to find a way that there's a function that it's 0 when we represent a cyclic configuration state, and it's 1 when it's a cyclic configuration state. But how we do this? Well, in a work done by Ramirez Renteria and Germán Rodrigo, they found that it's possible to map a cycle state as a multi-control Toffoli gate, as it's a junction of different configurations of these arrows or propagators. And as it's seen, this red multi-control Toffoli gate represents this kind of outer loop that is done. So first, to be possible to represent how to do this, to work with this kind of idea, we need to reduce the graph to a simpler graph. So instead of using these propagators, we utilize a reduced graph representation, in which ones we represent every propagator as an edge in a junction with the propagator that shares the same vertex. So first of all, for this kind of configuration, we use 12 propagators. We need 12 qubits to represent at least this diagram. Then, by using the reduced graph, we'll now represent every loop or each loop that is in the configuration. What we mean is every possible pathway that forms a loop in this diagram is represented by a clausel. And these clausels are equivalent to the circuit what we are plotting. But how would we determine the order of the gates and the number of ancillary qubits that we need to do this? Because if we try to do the different configurations in just few ancillary qubits, then we will have no proper solutions. So we implement something called the minimum click algorithm. It's a Grover-based algorithm that utilizes graph theory to be able to reduce the the parametrics, is characterized by two stages. This is the qubit reduction through close clustering, and the depth reduction by close grouping and optimization methods. Okay. So here we can see some of the different loops, and here we can see the diagram. Well, graph theory techniques. Well, in this part, we will introduce a little bit of the graph theory. We represent what is a clique, that is a complete subgraph, or we can call it is the kind of subgraph in a graph that has every vertex sharing with each edge. Like we can see, ABC is a clique, but DE is not a clique as DEC is not a clique as C doesn't have an edge with E. So we utilize the minimum clique partition problem that represents that we need to find the minimum number of cliques that is needed to represent fully a graph. And this is because the minimum number of cliques of the graph determines the qubit we need to use as ancillary. So first, in the qubit reduction, we have to represent the diagram with the different clauses as a graph that represents the adjacency matrix between each of the clauses. When one is the clauses that are mutually exclusive between them, and 0 is that they share a configuration. So this is like C0 and C3 negated are actually mutually exclusive because they can do at the same time as S2 and S2 negated is present in C3, so they can happen at the same time and makes no problem to do. So once we do this algorithm, we find the different cliques that are possible. We are represented in different colors, and then we have the solution of the different subgroups that we can use as an ancillary. Then we have the representation in the diagram and how each subgroup is represented as an ancillary. So this kind of idea reduces the qubits needed from 7 to 3 qubits. And to represent the depth reduction, we need to use the second algorithm to optimize the order of the gates. This is done by select the clauses that can be applied at the same time. So that ones that have no common edge, and clustering those that share edges that is possible, and exclude external loop clause. Well, now utilizing the same idea of the minimum clique partition problem, we can now represent the different clauses and in the matrix that represents the possible scenarios. So we have now these three, and we have these three groups principle that we have in red that are in type of clique, yellow is another clique, and the blue is another clique. Now we having this kind of cliques, then we utilize some machine learning techniques like the TPE problem to help us to encode an optimal configuration to have in the circuit. So now the results is now we have this pretty compact quantum circuit and theoretically, but we have some reductions in the different parameters that we need, like there's the total amount of qubits and the quantum depth. But we also apply a new idea once that you do the translation of the quantum area to represent how efficient is in principle a circuit. So once the translation is done, we have the difference in the quantum depth needed for doing the circuit, and we have a pretty outstanding difference between the prior work and this work, and the quantum area too. So what we found is that by mapping Feynman propagators to qubits, we can automate the design of the oracle for finding causality in the loop duality in Feynman diagrams. the graph theory techniques help us to determine forms of reducing the qubit needed to do this kind of work and to find the minimum depth possible. So, thank you.
So now we have time for a little quick question. Anyone? Well, I have one because in the last slide we saw that the depth is smaller than in the previous experiments. But
yep.
Do you think that applying more graph theories you can lower the depth in order to run in a few years in a real quantum computer, or is very difficult?
I think it's possible to implement some of these graph theory techniques to the optimization algorithms that are done by Qiskit, but we haven't implemented an opportunity to do this in the physical qubit sense, so it's a possible new work to do.
Okay, thank you. Thank you so much, Juan Pablo.
Thank you.
Now, our next talk is Aitor Arribas Hernández from the Escuela Técnica Superior de Ingeniería de la Universidad de Valencia. And he will talk us about the role of soft constraints in the optimization of driving protocols in neural atoms hardware.
Okay, so well, my name is Aitor, and I'm going to talk about that. So to give you a quick roadmap of this talk, I'm going to start talking about the maximum weighted independent set problem and how we map it into the neutral atoms hardware. Then I'm going to talk about the energy vanishing gap and how this threatens our optimizations. And then how we solve this by introducing physics-informed soft constraints. And then I'm going to talk about the evaluation pipeline that we've designed, the results, and I will end up with the conclusions and future work. So imagine that we have a graph where each node carries a specific weight, here represented by each side. You can think of these weights as a reward. So our goal is to find a subset of nodes that maximizes this reward. However, we have a constraint, which is that no two nodes of the subset can share an edge. This means that they have to be independent sets. Classically, scaling this problem up is a computational nightmare, but in neutral atoms processor, we can let the physics do the work for us. So here we have another target graph to our problem. And next to it, we see its physical counterpart, which is an array of neutral atoms, where the disposition of the atoms perfectly replicates the topology of the graph. To solve the problem, we drive the atoms with a global laser to the Rydberg state, and in this highly excited state, they are going to start interacting with each other via van der Waals forces. The interaction energy of this van der Waals force is going to scale up as the distance between the atoms to the power of -6. So when two atoms are close enough, representing an edge of our graphs, they are going to be effectively blocked to be excited simultaneously. This phenomenon, called the Rydberg blockade, is going to guarantee us that the solutions that we measure are going to be valid independent sets. And finally, to account for the weights of each node, we use a local detuning that is going to make some atoms more favorable than others to be excited based on their weight. So to sum up, we have a mathematical problem that we encode in the neutral atoms processors. Then we light the atoms with the laser to the Rydberg state. But due to the Rydberg blockade, only the atoms that encode the solutions to our problem are going to get there, and the rest we will find them in the ground state. And to do this, we use the adiabatic theorem. So basically, we start with an initial Hamiltonian where all the atoms are in the ground state. And by varying the frequency and the amplitude of the lasers, we transition to a final Hamiltonian that will encode the solution in the ground state. And here is where the theoretical physics crashes with the real hardware, since that slow pace demanded by the adiabatic theorem is inversely proportional to the energy difference between the ground state and the first excited state. And as our graphs scale up, this energy difference collapses into what we call the vanishing gap. So the ultimate question is how do we perfectly shape these driving protocols so we can avoid unwanted transitions and respect the adiabaticity. So a standard approach in the literature is to use an optimization pipeline. Usually, they are only fed only one objective, which is to maximize the approximation ratio. The approximation ratio is the ratio between the average cost of the bit strings that we measure in the number of shots and the cost of the solutions. And when we did this in our simulation, we found an interesting phenomenon, which is that the optimizer was able to find radically different driving impulses that achieved the same approximation ratio. So mathematically, all these solutions appear to be equally valid, but from the perspective of the real hardware, they're not. And this motivated our central hypothesis, so we need to find a way to break this degeneracy and guide the algorithm to the best solution possible. Therefore, we decided to introduce physics-informed soft constraints into the cost function. So by penalizing high derivatives and adiabatic violations, we encourage the optimizers to converge to a specific family of solutions, those that not only solve the problems in the simulation, but are also smooth, stable, and more friendly to the actual quantum hardware. These penalties operate through a threshold system, so basically, if the driving impulses fall in the safety zone, the penalization is strictly 0. But once we cross this red line, we start to penalize them. Each penalization is going to be parameterized by the weight that we assign to it and the threshold. And finally, the cost function that we fed into the optimizer is the average approximation ratio, since we can simulate more than one graph simultaneously, and the penalty that we associate to the driving protocols. In this project, we have defined 3 different penalizations that have been studied individually. First, we have the gap protection. So basically, along this evolution, the most critical part is going to be when the detuning crosses 0, since here is where the gap becomes minimum. And by encouraging the optimizer to maintain high amplitude values in this time window, we are able to keep this gap as open as possible. Then we have the slew rate, which is a term that was introduced by QTYR people in a paper to measure the adiabaticity. And finally, we have the 2-level adiabatic criterion, which basically means that we penalize the driving protocols if they don't respect the adiabatic criterion for a 2-level quantum system. Once we've defined our cost function and our adiabatic criterions, we need to evaluate whether these penalties provide an advantage or not. So we've designed this 3-stage pipeline. First of all, since we are restricted to use only 10-node graphs due to computational limitations, we need to start by mining for hard instances, since generally these are very easy to solve. Then we perform a grid search to find the optimal configuration of weights and threshold for each penalization. And finally, we validate this configuration by performing an optimization in 30 different graph sets. So here is, as an example, the grid search results for the 2-level adiabatic criterion. In the left panel, we show the approximation ratio obtained for different values of weights and threshold. And in the right panel, we show the penalty that was obtained for the optimal driving protocol for each configuration. And from here, we can select the optimal configuration based on the approximation ratio, and we can study these results in more depth. So here, I'm showing the performance of our top 5 hardest graphs. And the different colors represent the different penalization strategies that we've used. If you look to the orange box, this is the 2-level adiabatic criterion. We see that this is the one that performs the best in terms of median approximation ratio along all the graphs. Then the improvement, it's marginal, but we see that it's consistent along all the graphs. If you look to the green and blue box, which represent our baseline and the slew rate term, in this case, we see that the performance is the same, basically, in all the graphs, and these are generally the ones that perform the worst. And finally, we see that even though these are our hardest graphs, almost all of them achieve really high approximation ratio, so it's difficult to see a clear advantage of the penalties. Moving on to the generalization analysis, here, each data points represent an optimization that was run over a completely new set of graphs with the configuration that we found optimal in the previous stage. So here now we see that the no penalization is the one that obtains the higher mean approximation ratio. And the 2-level adiabatic criterion that performed so well before now suffers a drop in terms of average approximation ratio. However, we don't see a statistically significant difference between the distributions. But we do observe that we are suffering from hyperparameter overfitting. That is, the configuration that we found optimal in the grid search were too specific to the dataset that we use in that test. and the results, we are not able to generalize to other graphs these results. So moving on to the conclusions, we saw that the physics-informed soft constraints are able to, specifically the two-level adiabatic criterion, are able to regularize the optimizers and help them to converge to a better performing driving protocols. However, the generalization test showed that we are suffering from hyperparameter overfitting, which motivated our future steps. First, we would like to move away from isolated grid shares and implement rigorous k-fold cross-validation, so the configuration that we find not only achieve better results, but we can also generalize them to many different graphs. Then we would like to move to larger graphs, since I said these are generally harder to solve. The larger is the graph, the harder it is to solve. And finally, we thought about implementing new parameterization of the driving protocols, since using a more expressing parameterization could let us to get to a new family of solutions, a bigger family of solutions, where we could find better performances. And we think that if this family of solution is bigger, here the regularization of the penalties could stand out more. And that was all. Thank you.
So now we have time for one quick question.
So if I understand you well, you work with small graphs because you need to compute the gap. So essentially, you need to solve the problem, right?
No, we don't compute the gap. All this pipeline is thought that we don't need to solve the problem completely. We don't need to compute the gap or know the exact solution. We can help do the optimization without getting to that information. Because, for example, the idea is that we can use this pipeline for larger graphs, even though we don't have the exact solution. In real hardware, we could use this exact pipeline with graphs of hundreds of nodes.
So how do you optimize this if you don't know the?
Yeah, what we are trying to do is to optimize the approximation ratio, which is the mean of the. Well, here I didn't. Here, imagine that this is the distribution of the cost of the bit strings that you've measured. What we are trying to maximize is the ratio of the green line and the red line, which would be the red line is the exact solution. So you don't need to theoretically solve the graph. This is just the result of your measurements. So without solving analytically the graph, you are able to maximize, to use the pipeline.
Okay, thank you.
Thank you so much, Aitor.
Thank you.
Now, our next talk is David Aguirre. He is from the Basque Center for Applied Mathematics from the University of Basque Country. And he will talk us about the reconstructing functions for quantum states, a review, improvements, and a new Legendre-based method.
We have changed the order.
No. Sorry, Daniel?
Yeah.
Sorry, I have confused. It's Daniel Islamazón from the Euskadi Quantum Center, the University of Basque Country as well, and he will talk us about discretization independent efficiency for quantum Kalman Fourier algorithms. Daniel, the floor is yours.
Well, good morning to everyone. Thank you all for coming, especially today. I will talk about quantum algorithms for PDEs, and in particular, this talk will be about an efficient quantum Kalman Fourier algorithm for solving dissipative nonlinear differential equations. Okay. So, as you might already know, nonlinear PDEs govern a wide range of areas, including, for instance, fluid dynamics, plasma physics, and financial modeling. And in this context, classical solvers become intractable for solving these nonlinear PDEs when we have a large amount of equations or high dimensions, and we want a fine resolution for solving these kind of equations. And here, quantum computing appears to be an interesting alternative, given that by simulating unitary linear dynamics and under certain conditions, we know that we have exponential speedups for solving this linear system of equations. So the goal of this talk will be, if we have a PD, as we can see in the slide, the Burger's equation, can we map this nonlinear equation into a linear one with a bounded error, as we can see in this slide? OK, so the approach we will follow is the Kahneman-Fourier linearization. We part from a quadratic nonlinear PDE, and we discretize this PDE to obtain an ODE. We will use the Galerkin-Fourier discretization in order to remove, let's say, the spatial dependence of the PDE, and then we will linearize this nonlinear ODE into a linear ODE. We will use Kahneman linearization, and with this protocol, we will have an infinite linear system of equations. And what we have to do is to truncate this system to introduce this into a quantum computer and then solve it with quantum techniques. And we will focus on this first part before solving the problem with a quantum computer. OK. So the first step is the discretization of the nonlinear PDE. There are several ways to do this. And we have in the quadratic PDE, we have the linear operator, the quadratic operator, and the driving force. And using, for instance, finite differences or finite elements, we end up with a quadratic ODE, as I mentioned before, with a corresponding discretized now quadratic, linear, and the other operator. So for instance, so that you can understand how this discretization works, we can use this Burger's equation, one-dimensional, and we can select a given number of points in MS, and for each of these points, we can approximate the derivative of u, as we can see in the slide, and after doing some calculations, we end up with this nonlinear ODE, where we can recognize the linear operator, the quadratic operator, and the driving term. And the one we are going to use will be the Fourier-Galerkin discretization, in which what we do is to consider a set of the Fourier eigenfunctions. We expand the solution into this set and project, let's say like that, the equation into this set of eigenfunctions. And again, after doing some calculations, we end up with an ODE of this form, where again we can recognize the linear operator, the quadratic operator, and the driving term. So once we have this ODE and we have removed the spatial dependence, we have an ODE only with time, and we remove the nonlinearities, in our case, by using Kahneman linearization. In order to show how this works, we can see this example, a simple example, in which the variable is u. So what we do is to introduce or create new variables, y sub 1 and y sub 2, accounting for the powers of the nonlinearities of u. And we replace this into the equation, and then now we have a linear equation in the new variables y. The problem is that, as you can see, in y sub 1 appears y sub 2, and therefore we also need to solve the dynamics for y sub 2. Therefore, we end up with another equation for y sub 2, where now y sub 3 appears. So this is more or less the idea of this procedure, in which we can see that we have to create more and more new variables in order to solve the whole dynamics. And we end up with an infinite system of equations that are coupled, and that in this case is represented by the matrix A, which in this example it has this form. So we have removed the nonlinear part by an infinite system of equations, but now linear. So in order to solve this with a quantum computer, we need to truncate, to select a given number of equations of this infinite system. And what we do just is to select a C number of equations, the first C of them, and obtain an approximate solution of the original ODE. This is what we do. And in this case, we're introducing an error. We're introducing the Kahneman truncation error, which is the difference between the original, like solving the whole ODE with the infinite system of equations, minus the approximation we have for the first C components. So now I recover the question I mentioned in the beginning, is that if we can map this nonlinear equation into now this linear and truncated system with a bounded error. So in literature, what they typically do is to consider discrete systems, and they kind of give us a sufficient condition R, which kind of measures the ratio between the nonlinearity and the linearity part. The lambda 1 is the eigenvalue, the highest eigenvalue for the linear operator. Then we have the quadratic operator F2 and the operator of the driving. And what we can see is that if this condition is lower than 1, also with other more assumptions that we can see in the slide with the rescaling that we can always do, we can prove, well, it is proven in the literature that the solution norm is bounded by 1. And also that with this result, we have that this Kahneman truncation error I mentioned in the beginning is upper bounded by those quantities, where the most important one is that it's bounded by the norm of the initial solution, which is, because of this result, lower than 1. Therefore, if we have something lower than 1 to the power of c, if c goes to infinity, or if we increase c, what we have is that that bound goes to 0, or is reduced. So this is the idea. That we have the norm and the norm of our solution under control, and that we have proven the convergence of the Kahneman truncation error. Nevertheless, there is a problem here in this approach, given that this sufficient condition R depends on discretization choice. As we can see, for instance, in this plot, where the purple line represents like the limit. I mean, the Reynolds number is the physical parameter which measures kind of the ratio between the non-linear and the linear parts. And the purple line is kind of the best Reynolds number we can achieve for a given number of points in the discretization or in the mesh. And as we can see, if we want to increase, or if we want a fine resolution in our discretization, if we increase the n, the number of points, what we have is that we are only able to simulate low Reynolds number. This is low non-linearities. And this is quite a problem because this efficiency should not depend on the discretization, but only on the physics. Therefore, in order to overcome this problem, what we have done is to move this analysis to the continuum, to the Sobolev space, in this case the Hilbert space 0, 1. And we have formulated the linear operator, the quadratic operator in a continuum way, using periodic boundary conditions, and trying to obtain these two results, but in the continuum, without being dependent of the discretization. So in order to prove this boundedness of the solution norm, after doing some calculations, it is equivalent to find the condition such that y of the Riccati equation is that the derivative is lower than 0, because that y upper bounds more or less the solution norm of our problem. So the condition we have found in the continuum such that we have this boundedness of the solution norm is that one. Well, we can see that depends on the forcing size, on the nonlinear strength, and on the dissipation rate, but now this is independent of the discretization. And as we can see in the slide now, our solution norm in the Sobolev space A2, it's upper bounded by that magnitude. And with the rescaling I mentioned in the beginning, it can be set to be lower than 1. This can be applied to fluid dynamics. For instance, in the Brooks equation I mentioned in the beginning, we can again study the Reynolds number. And in this case, what we have is that we are able to simulate, under this constraint, Reynolds number up to more or less 40, which is quite an improvement with respect to the previous case, the same plot I mentioned in the previous slides, in which we can see that now we are able to simulate until that order of Reynolds number being this independent of n, which is important because of the reason I mentioned before. And also, just to conclude, right now we are also working on this Kahneman truncation error bound with this new condition. And as I mentioned before, what we did is to use the Fourier-Galerkin discretization, in which we consider the modes of the Fourier eigenfunctions. We obtain the corresponding nonlinear ODE as before. And then with this, the trick is that with this discretization, we have this inequality between the norm in the L2 space, in the discrete space, and the norm in the continuum. And using this and also more technical steps, we were able to prove that now with this, let's say, discretization independence condition, we have been able to prove that the Kahneman truncation error goes like this, more or less the same as in the discrete cases, but now mu was the nonlinear strength in the continuum, a physical parameter that doesn't depend on the discretization, and the norm of the initial condition is in the continuum, not in the discrete system. And this is more or less what I wanted to say. So the conclusions, as you might already think, quantum algorithms are still in their infancy. We have like a lot of things to do. And in this direction, what we have done is to prove these convergence and stability conditions for dissipative nonlinear equations based on continuum properties, being this independent of the discretization. So for future prospects, as you might think, there are a lot of ways of discretizing these nonlinear PDEs. So an interesting idea would be analyzing this Kahneman generalization for all these protocols, for all these schemes, and also trying to understand and to compute the quantum algorithm complexity, which depends, depending on the quantum algorithm, but depends on the condition number, on the norm of the Kahneman matrix, for instance. And regarding this talk, it will be also interesting to try to expand or to obtain a condition R lower than 1, less restrictive than the ones we have. And just before ending the talk, I would like to make some publicity to mention that we are organizing in Bilbao a workshop of this kind of topic, which is called Quantum Techniques and Algorithms for Differential Equations, QT8. And there will be here a lot of important speakers, such as Nathan Wave, Nana Liu. You can scan the code, and you are all welcome to come to Bilbao and learn about this interesting topic.
Thank you so much, Daniel. Anyone?
So maybe I miss it, but how do you understand the appearance of chaos when you do this truncation? Because in the nonlinear differential equation, you can have chaotic solutions. Right?
Yes, the thing is that we are considering dissipative nonlinear equations, and in this kind of equations, we don't. I mean, we are in a regime where we do not have so much chaos. Everything is more under control. So it's nonlinear, but the dissipative part is has more strength than the chaos part. So in the end, we can have chaos. But I mean, if we have more chaos, we have more linear part. We need a higher C, or more and more equations to consider, such that we have an important and interesting result. But in our regime, these are being lower than 1, with that kind of conditions, we do not have so much chaos.
But this lambda 1 that you wrote there in some of the conditions are somehow related to the some Lyapunov, because if you have some Lyapunov exponents or something like this.
Which lambda are you talking about?
There was some lambda 1. So I'm wondering if this appears in some way, this Lyapunov exponents or something like this.
Yeah, it's related to that. In fact, in our paper, in the paper of the boundedness, we call this stability the Lyapunov exponent, but no, it's like this lambda 1 is just the highest eigenvalue of the linear operator. I mean, a future prospect is also to trying to understand how this stability works with the Lyapunov exponent, but it is not related to it's just the highest eigenvalue of the linear operator.
Okay, thank you so much, Daniel.
Okay.
So now we have David Aguirre for Basque Center for Applied Mathematics from the University of Basque Country, and he will talk us about reconstructing functions for quantum states, a review, improvements, and a new legendre-based method. So, David, the floor is yours.
Thank you. So hello. As you can see, I changed the title because it was so long. So today I'm going to talk work in progress, efficient readout of genetic functions encoded in quantum states that I'm doing with my supervisor, Milton South. So the problem is, imagine that we have a quantum computer and we have an algorithm to solve any problem, but the solution of that quantum algorithm is this state that just we have a function encoded in the amplitude of state. Okay, so this is really good because we gain some exponential capacity because we can evaluate in an exponential number of points. But the problem is that the amplitudes of the function scale exponentially are exponentially small. So our goal now is to take out some properties of the function or even the complete function. So this is interesting in different fields like partial differential equations, and my colleague explained before, or even Hamiltonian simulation or quantum machine learning. And this is speed up that our quantum algorithms give us can be surrendered to the measurement step. That is the step that we are addressing here, as Aronson said once. And well, the thing is that we are not trying to take out to learn a generic state. We have some properties that we can exploit. For example, smoothness, periodicity, locality, or sparsity, or the low rank of the function. So before going with the methods, I'm going to explain just two tools that we are going to use. This is the Hadamard test that allow us to calculate the inner product between two states. And this is going to be similar to doing a Riemann sum, and this Riemann sum is similar to doing an integral, as you know. And the other one is quantum amplitude estimation that allow us to estimate the amplitude of a state in linear complexity with the precision instead of quadratic that will be just doing some measurements, okay? So I'm going to do like a really fast review of existing method, and then I'm going to go with my contributions. So one of them is the naive approach of just taking the state and doing measurements and computing and counting how many times appeared each bit string, and then reconstruct the function like that. Okay, so the problem of this method is that we can just reconstruct or rebuild this function if it's positive, and the problem is that the sampling and counting is just an exponential method. So we can improve it a bit with this quantum amplitude estimation and the Hadamard test. The Hadamard test allows us to remove this positivity, and we can just learn complex or positive and negative functions. But the problem is that, well, we have this quadratic speedup, but it's still exponential in the number of qubits. So the good point of this method is that we don't need assumptions about f. We achieve this Heisenberg limit with the quantum amplitude estimation, and it's efficient if f is localized, if we have only a few amplitudes that are not 0. And the limitation, again, is that it's exponential. The first method that is not exponential is this Fourier space readout. And the idea is to go from the usual basis that we express the function to the Fourier basis. So we apply the quantum Fourier transform, and we will have a state that gets in the amplitude, we have the components of the coefficients of the Fourier expansion, okay, this C sub k. So if the function is p times derivable and is p times periodic in the derivatives, then in the derivatives, then we will have these results, that this complexity that now scale like quadratically and a factor that depends on the smoothness of the function. And if we use quantum amplitude estimation at the end, we will even improve it a bit. But well, right now we have this polynomial complexity that is better than the exponential one. We can extract sign and complex functions. But the problem is here that when we don't have periodicity, the complexity scales to the power of 4. Okay, so we can even improve this method. Another one is the Chebyshev method. It's almost the same. We go to the Chebyshev basis instead of the Fourier one, and this allows us to remove this periodicity that we needed in the previous method. And well, the Chebyshev polynomials are built like that, and then we can express the function in this type of basis, and we can extract the coefficients doing, again, this Hadamard test, and this is similar to doing an integral, okay? The problem here is that for doing this, we need to have our function evaluated in the Chebyshev nodes. The Chebyshev nodes are these ones. We can build it like taking the semicircle and putting each point uniformly across this, and then taking a vertical line to the real horizontal line, okay? So as you can see, the Chebyshev node concentrates in the limits, in the extreme limits. And this is not usual because the algorithms that we usually have evaluate the function in the uniform grid. So this method, it's better than the previous before because we don't have this periodicity condition. We just need smoothness. And even the complexity is lower. But we have this limitation of Chebyshev node grid that is not the common way that we have our function. So there are a lot of other works that I'm not going to focus on. But just we have some tensor networks and orthogonal expansion that consists in trying to approximate this function with tensor networks. Then some other overlap filter extension that use these Lorentzian functions that are not completely general. Some problem-specific bases that use some classical simulation. And finally, some QML readout that instead of trying to extract the function, extract some properties of these functions. So my first contribution is to improve a method that already exists and consists in doing again Chebyshev, but in this case it's not a spectral method that we change the basis. It's more like interpolation. So we go with the observation that the probability of measuring just a state that is less than this k, a k can be whatever, is similar to doing that Riemann sum, and this Riemann sum is similar to doing this integral. So we can evaluate the integral of the function to the square, okay, the square of the function. So this f can be interpolated at the Chebyshev node, and then we can do the derivative and the square root, and we can obtain just the absolute value of the function. Okay, so this method explained for analytic functions, and if f is analytic and all the derivatives are bounded by a number, then the complexity scales like this with this logarithm factor. So my contribution is just to extend this to any type of function that are not analytic, can be just smooth. And using Hadamard test instead of measuring, just like this, we can extend it to complex numbers, not just positive functions. And well, there are some limitations. One of them is that the derivative introduces some error doing the derivative that is classical. That is the classical part of the algorithm, and that interpolation is less robust than spectral analysis, as I explained before. And the last contribution, and I think the more important one, is this legend coefficient instruction. So the idea here is instead of going to Chebyshev basis, go to legend basis, because this legend basis is orthogonal in this uniform grid. So the legend polynomial can be built like that, and they satisfy the orthonormal property. And we can, again, expand our function in this basis. And we can compute these coefficients doing this Hadamard test again. But there is a problem. We need to encode this polynomial, these legend polynomials, into a state. And the legend polynomials are the five first ones are there. As you can see, all of them goes from -1 to 1, and that's a good property. And the good point is that we can do it with some techniques like block encoding or quantum singular value transformation, that are new methods for encoding function into quantum state. And as you can see here, in the infinite norm, we can achieve a complexity that is scaled linearly, almost linearly, if the function is really smooth, or is smooth at least. The limitation here can be that we have this complex test preparation, but we can do it in pre-fault tolerant era, because all of this is for pre-fault tolerant era. Okay. So, well, here is a summary of all the methods and complexities. And the other contribution that I give in this work is the decision guide. Depending on property of the function, we can decide what method used for extracting the function. So, for example, if we just need properties of the function f, we use quantum machine learning method. If f is not smooth, some tensor networks. If f is smooth and periodic, we can go with Fourier. If f is localized, just some amplitudes are different than 0, we can go just with measurements or measurement with quantum amplitude estimation. If f is in the Chebyshev grid, the method with Chebyshev. And finally, if F is smooth and in the uniform grid, that is the usual case, we can go for this legend coefficient. And I say that this is the usual case because this is useful for PDEs, and PDEs usually have these smoothness properties. So this is the method. Finally, just to say that all this method can be extended to multivariate functions, and it's usual to see all the methods explained like this. And we can also improve this or extend our contribution to this regime. So I have proposed a new method for extending these functions. I also have given us some guideline of what method used for every type of function. And there is an open question now that is, can we determine the most suitable extraction method when no prior information about the target function is available? So it's an open question that right now I'm working on, and that's all. Thank you very much.
Thank you so much. So now we have time for one quick question. Well, if no, I have one, because you said that the Chebyshev one was the interpolation was less strength than the other one.
Yes.
So what do you? Yeah, that less robust than the spectral analysis. So
Yes.
what exactly do you mean by less robust?
When you try to, I mean, the method of calculating the coefficient of the Chebyshev expansion is usually introduce less error, but is less error than doing the interpolation. But the thing is that in complexity is the same, but this coefficient that is usually with the complexity is not the same. It's like it's the error here could be the double of the compared with the spectral one. So it's just like a limitation of the method, but it's not really important because we are all the time talking about complexity. So anyway.
Okay, thank you.
Thanks.
Now, last but not least, we have José Javier Orquín Marquez from the University of Valencia, and he will talk us about analog quantum feature selection with neutral atoms quantum processor. So,
okay, thank you so much. Thank you so much. My name is José Javier Orquín. I'm going to talk about my last work on quantum feature selection on neutral atom quantum computers. I will start with a brief introduction about what is a neutral atom quantum computer, what is feature selection in machine learning, and how we encode this kind of problem in hardware. I'll start saying that feature selection is a crucial problem in machine learning, in which we have a data set with a lot of different features, and we always want to select or find the best features or the more informative features for this particular data set. This kind of problem, when we move to bigger data sets, is an NP-hard problem, which usually is solved by forcing or using greedy algorithms. But neutral atom hardware and its behavior can help us solving this kind of problem in a very natural way. Feature selection actually works with this formula we find here, in which we have two very important quantities, which is the importance, the individual importance, and the redundancy. The individual importance is the quantity we measure that measures the information that is shared between the target and the individual feature in the data set. Also, we have this redundancy metric that measures how these two features, every two features in the data set changes and which information are shared between those features. That's why we call it redundancy. This is very important because we are going to introduce or to encode this cost function in our hardware. Now I'm going to talk only a bit about neutral atoms because I told my colleague already done a brief introduction. we basically have to prepare an arrangement of atoms. We can select the particular positions of all of them, and we have to program a particular driving protocol which drives this arrangement to particular solutions we are interested in. This is the complete formula, the complete Hamiltonian for this neutral atom hardware, but we only want to focus on the control parameters, not going more into detail. We want to tune the omega parameter, which modulates the superposition and opens the system to different solutions, and also the global and local detunings, which makes each of the atoms to be activated or not. Of course, the global detuning acts on all atoms at the same time, and the local detuning acts on particular atoms we can select. It's very important to talk about the reader blockade mechanism, because this behavior is what we are going to use to actually find a particular selection of features. This phenomenon is very important because what we observe when we put two neutral atoms very close is that they cannot be activated at the same time. We can take profit of this and compare it or make an analogy with the redundancy term of the neutral atom. And this automatically leads us to a configuration in which two features or atoms that are very close or very redundant are not activated at the same time. And that's the way we can find this less redundant combination of atoms. This is the protocol we actually use for this particular problem. We saw that the blue line is the omega parameter, which creates superpositions and open the system to different solutions. We start the protocol with a very negative global detuning, which initializes the system on all atoms deactivated, and then we move forward in time and found that at the middle of time we put off the global detuning, but we put on the local one. That's why we are going to use this local detuning modulated as the importance of each variable. And this, together with the correct positioning of each of the atoms, creates or encodes the feature selection problem in the Hamiltonian of our system. How do we embed this problem? We actually take directly the redundancy matrix of all features. We take all the individual redundancy between all pairwise features, and we translate it directly into positions in the way that when two features are very redundant, will be very close in the arrangement. Of course, there is no perfect way of embed this, because it's very common that the theoretical positions we have to have in the system may not be Euclidean, since we are working in a 2D matrix. But the important thing is to try to maintain the more redundant pairwise features. For example, when we have two more redundant features, it's very important to be very close, but it's not that important when two are not very redundant to be very separate, because the reader blockade mechanism works only on very near fields. Then, when we have this driving protocol prepared and the array is prepared, we only have to do this quantum evolution, and when we measure, we obtain something like this. Here we can observe each of the features. It's only an example, but we can see all the features of the dataset. And the read-write density is the probability or the ratio in which this particular atom or feature is activated. So we can analyze this and directly observe it as a importance of each of the features we want to check on the final dataset, on the final subset of features. We usually have to do a very not very technical but very important post-processing, because it can happen that due to these errors in the positioning that we cannot make perfect arrangement, we can find particular solutions in which we select a lot two very redundant features. So we perform a very simple post-processing that finally filters all the relevant solutions. Now I'm going to move to the results. We have tested this with 3 different datasets of different problems, one of bank marketing, adult income, and churn. And we measured the performance with these 3 metrics and compare it to classical feature selectors. What we observe is that the quantum feature selection algorithm achieves competitive performance with the classical counterpart, and even in very particular cases, mainly in the smallest feature set size, we found that the quantum, which is the green line, outperforms the classical benchmarks in some of the subsets. This is a small table in which we show exactly which particular subsets does the quantum feature selection algorithm outperform the classical counterparts. Yes. And as the conclusion, we observed that we were working on a very natural way of solving these kind of problems. We are taking advantage of the quantum behavior of this kind of systems to solve a very complicated or a very combinational problem. The way we map this is the only classical algorithm that we have to use to translate this redundancy into positions. And we observe that the performance is close or in particular case outperforms the classical parts. As a future scope of this work, we want to actually evaluate the noise or errors we can find in hardware with simulations. And actually, we would like to really implement this on real hardware, and also try to test on different problems, such as, for example, portfolio optimization or other kind of combinational problems. And if you want to check my article, is uploaded in archive. So yeah, that's all. Thank you very much.
Thank you so much, Jose Javier. Now we have time for one quick question. If not, I have one. Okay.
Thank you. First of all, thank you for the nice talk. I was wondering about this post-processing part that you said that it was not very technical but very important. So I was wondering if you could go a little bit deeper on that, just as curiosity.
Yes. As I said, when we create this particular arrangement of atoms, we cannot create a perfect arrangement of atoms. And can happen that two atoms that must be very close, it's it's not possible because the way it creates the way the algorithm works is creating the arrangement that respects the more the error between the theoretical positions and the ones we actually have. And can happen that, for example, if we have two atoms that have to be very close and the second atom have to be very close to a third, but this third have to be very near, very lejos from that, yeah. This solution is not compatible with the Euclidean distances, so we may have this atom very close, but may not be that close, and that could lead to solutions that are still a bit redundant in some particular cases. So we have post-processing that filters that kind of problems, basically.
Okay, thank you.
So thank you for all the speakers, specifically.
Thank you.
So now we are finished and we have time for lunch, and we come back at 2:30, I think.